is small, then the cooling is described by a classical law, Newton's law of cooling. It says that the rate of change of temperature is proportional to the temperature difference. And this equation, when you integrate, you find that the temperature decays exponentially fast to the environment. And then this K here is a system parameter. So the initial condition comes during the creep factor. And larger the creep factor, more the time it takes to equilibrate. And so if I plot time to equilibrate versus the initial temperature difference, it is a monotonically increasing function. This is what you would all expect intuitively. Cooler sample, it gets faster. Now, when this experiment was done, just to repeat the experiment, take water at different temperatures, put in a freezer, and measure freezing time. So when the experiment was done, so on this axis is the initial temperature, and this is the time for freezing. And as you increase the temperature, the time taken comes down. So this data is from Mpemba in physics education article. He was a graduate student. He was a class finishing high school student at that point of time. And this paper is written in a very easy style. And when you read that paper, you get a very nice feeling. So this effect is named after this author. So what is the effect? Water samples freeze faster. Now, that is quite an old experiment, but there have been multiple experiments on water since then. And so I'll just show you two examples. In this example, again, the initial temperature here, time to freezing, and you can see the water sample takes a less time. Likewise, here too, the water sample takes this time. There are counter experiments counter to this also, which I have not shown, but mostly this is a reproducible phenomenon. So for water, multiple reasons have been suggested. For example, there are many papers with multiple reasons. For example, one would argue it is because of hydrogen bond structure being more important than lower temperatures. The previous one of those graphs below like argued that if you remove gases that are dissolved, then the effect is not there. Hydrodynamic, supercooling, impurities, and so on. Many reasons have been suggested. And the effect, cause and the effect, both are water specific. But there does not seem to be any consensus for water. So I will put this explanation category under hidden variables, meaning it says that if we introduce one more variable, temperature, and one more axis on the other side, it says how much gas is dissolved. Maybe in this complicated phase space, there's no crossing of, there's no such, if I look at the multidimensional phase space, maybe such faster cooling is just because the initial system is closer to the steady final answer. So, in a more general scenario, you can ask, suppose I have a system which is out of equilibrium or in equilibrium. So, I have a final steady state to which I quench. I have one system which is hot, one system is warm, and this system is further away from the steady state, and this is closer. That is a statement that has to be quantified. Then you quench from the initial state to final state and ask what cools faster, the hotter or warmer. Now, this further and closer, if you want to quantify, you need some distance measure. So let's assume there's some distance measure which says distance from whatever is the current probability distribution to the final steady state. There is a function like that. And then if I plot this function and I start something far away and they cross, this is equivalent to what the Mpemba saw, and this we'll call as the general Mpemba effect. And this slide I put just to show that the effect is not water specific. Many different systems, so magnetoresistance, carbon nanotubes, they all claim, and many more experiments, they all show this effect of system is further away, integrating faster. This is an experiment on colloidal systems. I'll describe this a bit more in detail. So then, so then you can ask, how do I study Statphys effect within simple models? So this paper sort of made this phenomenon quite popular. And, so let me describe what their argument was. So the argument was, suppose I consider a rugged potential which has a lot of minima. So let us say there are 3 minima, E1, E2, E3, which are at different times. So, so they idealize this, keeping this in mind, they idealize the system with a 3-stage Markov process in which there's energy E1, E2, E3, and rates of going from one to another, which will be detailed values. But this rates has an Arrhenius form that they have to cross a barrier to reach. And for this simple system, they were able to show that if I look at a certain well-defined distance measure, then the hotter object initially is further away from the steady state, and as time goes on, it reaches much faster. So their argument, what they try to argue is that generally the model is made in a manner.
Sorry, this is true. It is the peak heights are reached, like the first peak is lower at last second.
Yeah, yeah. So they have the general argument. So this is what the argument is, that suppose I have 2 minima, and then my temperature in the end is so low that it prefers this minimum most. But there's intermediate temperature where this is populated a lot, and there's a high temperature in which things don't see this minimum. So when I quench from the high temperature, it does not get trapped in a metastable state and just drops into this one, while the system that is intermediate energy gets trapped here and takes long. So this explanation is quite appealing and intuitively it's appealing.
And Rajesh, in that dynamic Arrhenius rate equation, the temperature that comes, does it also change with time, or is it the initial temperature?
So if you start the initial condition no, this is the final bath temperature. But you start the system in 2 different temperatures, TH, equilibrate the system in that, and then do the dynamics with the bath temperature, TB. Okay. The final quench temperature, T. So then there was this experiment that clearly showed the effect in a single particle problem, and the explanation is through metastability. So what are the experiments? So they considered a double well potential asymmetric in which a colloidal particle is trapped, and they can control. So it's a double well which is cut off in the left and right with up to infinity. So it's trapped in this x min to x max, and there is a 2 minima which is asymmetric. And then in this experiment, they could do this quenches thousands of times and actually plot the property distribution as a function of time. So, for example, if you look at this plot, so they start a system at high temperature. So they have a cold temperature, which is the final quench temperature, and this is the initial property distribution of the particle. Then, as time evolves, it relaxes to finally the final equilibrium answer at this temperature. Similarly, for the warm, you have an initial distribution which is slightly more opposite to the 2 edges, and then it also equilibrates. So what they're able to measure is the probability distribution as a function of time. Then they looked at the difference between this probability distribution, that is the distance measure, and they clearly show that the hotter object moves faster, and the warmer object takes a longer time. And this is very conclusively, there's no ambiguity about this. And they also show that if you choose the parameters appropriately, then the hotter system cools exponentially faster than the cooler system. This is called the strong Tensor effect, and it was argued in the other paper also. Okay, so now let me tell how to define Tensor effect a bit more unambiguously. So consider some Markov process. So Markov process is defined by giving a set of configurations and the transition rates between them. And then what you track is the probability of a configuration as time t. And then you can write this expression as a function of the eigenvectors of the transition matrix. So this is the long time steady state. Then there's the first excited state with an eigenvalue λ2 and λ3 and so on. So if I wait for long enough time, all these terms drop and you get the steady state answer. Now, λ2 is a system parameter. It's determined only by the rates and not dependent on the initial probability distribution. The only place where the initial distribution comes is in A2. So A2 is the inner product of the first excited state with the initial steady state of whatever I prepare in the system. This is the only parameter. This is a function of the initial state. So initially, some hotter object is further away, and then I find at some point that this A2 for the hotter object is less than A2 of C, then the hotter object equilibrates faster. So that is what I'll call this right. So I just need to calculate this A2, this coefficient, and ask, does a hotter object have less A2 than a cooler object? And I will get a term by.
But the relaxation rate would be same.
Relaxation. So in this, the lambda would be the same. So the effect is in this A2. Of course, if A2 was 0, then it checks. So that I'll come to that next class.
And you would need then in this presence of discrete spectrum. But if you have a very large system,
Yeah, so
in the spectrum,
then you know, so anyway for the last spectrum is not computed. I'll just remark on that next time.
Rajesh, is it possible all more? Can we answer questions later because the time is too short, right?
No, time will not be too short. I finish on time.
Okay, fine.
So if I were to plot A2, so if I fix a bath in terms of the bath temperature, fine. If my bath temperature is measured in terms of bath temperature, if I were to plot A2 as a function of the initial temperature, and it has a non-monotonic behavior like this, then I can choose the high temperature to be this one. So I get A2H here. I can choose the low temperature to be here. I can get a higher A2 cold, which satisfies the criteria for temperature. On the other hand, if I have some A2 which behaves like this, I will shift them back to this axis. Now, then I can look back at this expansion and I can ask what is strong temperature. The strong temperature is if I put this, if I choose my temperature so that A2 is 0, then it decays with the next eigenvalue, so it decays a bit faster. So therefore I can always, if it's possible to find this criteria, then a hotter system can include exponentially faster, and therefore it gives you an avenue to faster equilibration in principle. So now you can ask, is this definition practical? So the definition using A2 is unambiguous. But you know, the moment number of particles increase, the system becomes more complex. Calculation of A2 is almost impossible. I mean, you may be able to compute λ2 with difficulty, but A2 seems almost impossible to compute. Hence, the use of in this experiments like temperature, magnetization, those experiments that shows thermodynamic quantities you use and look for their crossing. Are these two definitions compatible? That is not very clear. So now I'd like to ask the following questions. So what is the explanation of temperature? So I have argued that the metastability seems to be an appealing and popular description, explanation for metastability. Now, so I will in this talk address this particular question by asking, is metastability necessary? Then if time permits, I'll ask what is the role of activity in this effect. And we have looked at these other questions in other things. If I just mention in the conclusion if I keep time. So, so the problem we looked at was a colloidal particle in a single well potential, where the potential is linear. So we have a linear potential here, a linear potential here. There is a the derivative is discontinuous. So why this? And then there's a particle trapped in this potential. So why this example? This example, firstly, potentials like this are explicitly explicit, and an explicit solution can be easily constructed. So you can actually solve for many things exactly for this potential. Secondly, the single well potential has no metastable minimum. So then you can answer this question. If I find Pepper effect here, is a metastable state a necessary condition? I can answer. And the answer is no. Of course, the answer is no, because otherwise this question will not come. So there's one slide. So we consider a overtime Langevin equation. So this is the potential, this is the noise, and the corresponding Fokker-Planck equation. It is not, none of these come into play so much. And then we find the solution for P of xt as the ground state plus the first excited state and so on. Okay, so the point is we can construct for number 2 or for sub 2. So the computation of A2 is easy to do. That is the point. So now we call the criteria. So we just need to compute A2, which is this overlap integral. We know psi 2, we know the equilibrium distribution at any temperature. So the integral is easy to calculate. And we are looking for this criteria, and there's a non-periodic behavior. So first, I just want to so let me one more. I come back to the potential. There are a few parameters here. So in the non-dimensionalized variables, there is a length which we take 2 pi from here to here. And then where this minima comes, divides into 2 regimes, the right and the left. And the ratio of that I'll call alpha. So that alpha is the asymmetry between the length of the right domain and left domain. Alpha equal to 1, equal. Then there's a UR, which is the potential at this side, UL, the potential at this side. So there are these 3 parameters. So first, I'll argue metastability is not necessary. For that, I will just give one example. So consider a potential like this, and I consider a potential which is like this at the blue. 2 different ones. For the blue, A2 looks like this. For the red, A2 looks like that. So that is the proof. That's not proof. This just says temperature. I can just choose a temperature here and temperature here. I get temperature. The bottom is inverse. It says that if you heat up the system also, the cooler system heats up faster than the intermediate temperature. And to show an explicit construction, if you construct the distance of these trajectories, the hotter object crosses the distance of the hotter object to the final solution crosses the other one. So that's a crossing. So that is just extra evidence for the fact that there is a Pemba effect. So I just showed one example for the existence of Pemba effect. But I can ask, is this effect generic, or did I tune the parameters a lot to obtain? And if fine tuning is required, then you can still say that this is just a cooked up example. So then we find the phase diagram. So so there are 3 parameters: UL, UR, and alpha. Alpha is the asymmetry. So for example, if I fix alpha equal to 1, and then I look at in this regime, there is a sizable regime where I can find Pemba. That's why if I change alpha, and the point of the slide is that it is not generic. If I just randomly choose a particular potential, I'll be able to find Pemba. So and then details that strong Pemba can also be found. Point is, it is just any system you take, at least this system, you can always find very easily.
Is there a region for inverse Laplace?
No, you can. There is of course there's exactly you can construct exactly similar thing for inverse Pemba.
So this channel type thing, is it because that it becomes symmetric?
For the fully symmetric potential, there is no, because you know that you can show that for the fully symmetric problem, you cannot have. This was just to demonstrate that we had taken this linear potentials, but experimentally you have harmonic potential. So we just took an example with the harmonic potential, solved numerically, and showed that you can have temperature. So that you can realize this in the same experiment that I showed in the beginning. This potential can be created. So now, I should finish 5 minutes before, or
No, yeah, you have still 3 minutes. More than 3 minutes.
so for the double well potential, there was a particular study of this, including activity for the coronal part. When you include activity, the boundaries get more populated, and then they showed that in a particular case where the passive particle did not have temperature, you can have a temperature for the activities. So what is activity? So the same equation as before. Now you add a term for telescopic, so whatever we call it, the velocity, and in a direction which flips every now and then. Now the equations become a bit more complicated, because you have the probability of left moving particle, the right moving particle, and then you cannot solve them with this potential. You have to solve new. So activity can go either way. So for example, in this case, if I look at no activity, that is V0 equal to 0, this A2 is non-monotonic. When I increase activity, at some point, the activity goes away. Activity goes away. The non-monotonicity vanishes. So activity can reduce temperature. On the other hand, in this example, when I put activity, I can create. So it seems you could take something and look at it. When you look at the details, you can get whatever you want. And then you can construct this complicated phase diagram. How the phase diagram changes when you include activity. So this all work we are doing right now, and maybe some pattern will emerge, but I do not know. It seems like it. Okay, so let me summarize. So temperature effect is a counterintuitive phenomena in systems relaxing to steady states, and metastability has been an appealing and plausible explanation. But what I argued is that metastability is not a necessary requirement. In fact, temperature is generic in a single value potential, and activity, role of activity also can go this way or that way. So there is no particular conclusion. So somehow the single value result is very disappointing. Meaning it would seem that the whole effect is just some in the details of the initial space. So we are trying to see whether there can be more thermodynamic explanation of this by looking at when you relax entropy production, work extraction. I'm just throwing some words. We have not done anything. We are just thinking in this direction. That can we have a more explanation in terms of thermodynamics? Then the strong temperature effect gives a pathway to faster cooling. So you take a system, you heat first, then it just cools extremely fast. So we are interested, but heating takes some thermodynamic cost. So we are trying to ask the question, what is thermodynamic cost for doing such total cost? Again, we have not had, these are just questions we are interested in. And finally, what is the particular reason for water? Water is a complicated system. So maybe one way of doing that is to ask, if you find temperature effect, if I do other fluids with doesn't have hydrogen bonding and so on, to ask what is a generic reason and what is water specific reason. So we have been working on this for some time on this system and on granular systems. So Apurva was my student, and the other work is my collaborators are Prasad in Cochin University, Oren in Weizmann, Karnad in IMSC, and these are some of the papers we have.
Okay, so let's two vessels and discussion
So
sessions.
there's a lot of that.
Okay. Fine, let us start with Raja because I have to.
No, it's fine.
We both will ask.
So,
Thanks for the wonderful talk. So I had this question. So in the initial expansion, you showed is it possible that all the modes may not be there depending upon the initial temperature of your system?
It is possible, but in the long time limit is what you're looking at. You're asking ultimately what reaches first, and that is controlled only by others. All of them that whether they're present or not, they die off.
But is it a function also of the heterogeneity of the system or the medium that you are interested in that? For example, A2 may not be there in your system in the initial configuration.
So that is what I was calling strong peptide.
Okay.
A2 was not there, so this is the strategy that you find pathways where you kill A2, you find a manifold which has no A2, and then you take it there, and then you can have faster cooling. Many protocols of
Thanks.
Okay, thanks.
Maybe fully understand. So the 1D example, there's one minimum example that you said.
Yeah.
You have two slopes
yes.
different. And in the case of water, is there any reason to assume that or expect that there will be two different slopes depending on the?
No. So water was only the motivation. This has nothing to do with water. See, water, for example, you're measuring temperature. Suppose I feel if you introduce, there are many other features, there's a dissolved gas and hydrogen bonding and so on. So when I plot this multidimensional phase space, then I can ask, in this multidimensional phase space, what is my distance pressure? So I define a proper distance pressure in that. Maybe there is no crossing. Maybe there is a crossing. But now that I feel that this is a generic thing, it just seems to be depending on the initial conditions you choose. So maybe that also is not necessary. So I'm saying that if I have multidimensional phase space with project onto one dimension, you can have crossings coming quite easily. It could be that also.
Okay, thanks.
So how common is inverse effect? I mean, is it common experiments?
Oh, experiment somehow the people all look at the smaller one. I have not, whatever I've seen, ones that went from higher one. But I don't see any reason why. So numerical papers more.
No, but existence of inverse Plumber already tells that this what you call metastable explanation is not may not be correct.
Okay.
No, because if it settles into the minimum, then there is no way to there is no reason why one of from the minimum we pick it up to go to the higher.
No. Rajesh, thanks for a very nice talk. You commented that asymmetry in the U's are necessary, well and UR. But for more asymmetry, there is less FFR.
That I wrote somewhere there.
Yeah, but is there then any kind of optimal asymmetry that will give you the effects?
Well, I just wrote that to say that.
This slide.
So keeping this UR, when I increase asymmetry in the domains, so in that original nature paper, they claim that when you increase this alpha, the perfect is easier to see. But when you look at this plot, the area that shows the perfect sort of decreases. So that is why, but I just sort of stressed that. But that was good.
Just one simple thing. The A parameter, in physical sense, what does it mean?
It controls your relaxation. Physical sense.
Like in a, let's say you were saying the water and let's say different other materials. So comparing the same phenomena in different materials, how do you relate to the material property? That's what I'm saying.
So once you write if you make a mock, you have to idealize. Maybe somebody else can have a but I would say that once you have a system, whatever system you take and you put in some dynamics for evolution, then that is unambiguous. Then that A2 comes unambiguous. Now, if you put a different dynamics, I'm sure you get a different answer. So that part is, that is. Maybe somebody else is a more profound answer.
But I just have one more short question. So from what you said, it seems that the metastability appears to be this is sufficient condition, right, for implement.
Yeah.
If so, then it should happen in freezing and many other
Yes.
conditions where
So-
there's a metastability, right?
So in fact, in there's a lot of study about spectrum in icing model and so on across the transition. To find it.
Okay, okay. And so it should be for freezing.
Yeah.
Just for freezing.
Freezing in some examples when they do find, and that is related to this metastic.
Yeah, that's what I'm saying. So it's a,
But there are some ambiguities about, so I can stress, there are some ambiguities about using this thermodynamic quantities as a criterion.
okay.
Because in the render system, we try out many examples of how to use a distance measure. And then the effect itself is dependent on the distance measure. So one has to be careful to know what one distance measure shows trend, I think the other one does not show.
Oh, I see. Okay, okay.
So you have to be a bit careful with that.
Okay, so let us thank the speaker. We don't have time to take any more questions. You can ask anything, right? So our next speaker is Prashant. So Prashant is 12+3, okay?
All right, so I would first like to thank the organizers for giving me this opportunity to talk here. So I'm going to talk about some thermodynamic aspects of stochastic systems. And more precisely, I'll tell you about a way to estimate entropy production in an experimental friendly way for time-dependent systems. And it's a work done in collaboration with Karen Grossman, who is also from the Sport Institute, where I was. Okay, so first, let me introduce, remind you what the standard thermodynamics tells us. So firstly, it deals with microscopic systems, and it tells us about the rules that govern the conversion of one form of energy to the other in these microscopic systems. We have, for example, the first law, which is the statement about the conservation of energy. And the second law, which tells us that in any process, the total entropy change of the universe, which is given by the system's entropy change and the environmental entropy change, is always non-negative. And moreover, all these quantities are deterministic quantities, which means that if I repeat the experiments, the values of these quantities remain the same. So over the last 2 decades or slightly more than that, there has been development of a framework which allows us to study the thermodynamics of stochastic systems where thermal fluctuations are important and which can be arbitrarily away from the equilibrium. And as an example, we can think of a overdamped Langevin equation where the motion of the particle is described by this equation here. The U is the conservative part and some non-conservative force which might be acting on the system. And this X can also be a vector, which means you can have multi-particle scenarios as well as high dimensional setting. But in this talk, I'll just focus on one particle, but one can extend those ideas in those complex scenarios also. All right, so if you solve this equation, then you get different trajectories, and stochastic thermodynamics allows us to associate these thermodynamic quantities for each of these trajectories. For instance, the heat associated with the trajectory is given in this way. This is the force acting on the particle from the bath times the displacement integrated over the final time. And the work is given as a time derivative of the conservative part plus a contribution which might come if you have some non-conservative forces acting on the system. And once you make these identifications, then you can have first law at the level of single trajectories. And these quantities, these X here are the trajectories, which means that these these quantities, the heat and the work, are the stochastic variables. One can also go one step ahead and talk about entropy, and obviously talk about entropy, to talk about the systems entropy and the environmental entropy. So for environmental entropy, I'm going to assume that the system is in contact with the heat bath, which is at a well-defined temperature T. So the change in the environmental entropy can therefore be written in terms of heat in this way. On the other hand, the system's entropy is given in terms of the probability distribution. This is mostly motivated from the Moivens definition of entropy. And here the X that goes into this distribution is again a stochastic quantity. So this is also a random variable, and this is also a random variable. And the total entropy change is given by the sum of systems entropy and the environmental
Is
entropy.
there a P basic in the system entropy?
Sorry?
P log P we have for the
No, when you take the average, that P comes, but this is at the level of one single trajectory, so it's just this. All right, so for the overlap systems, one can show that the average of this quantity is given completely in terms of this V function here, where V in turn depends on all the forces that might be all the forces acting on the system, plus this contribution from the distribution. And so this is the average of V squared, and which means that this quantity is always positive. So so stochastic thermodynamics tells us that the total entropy change on average always increases. And it's a zero only for the equilibrium case, where the distribution is given by the Boltzmann distribution. In fact, if suppose you want to measure entropy experimentally, then implementing this formula directly turns out to be difficult, because one then has to know like what this force is. But just from the experimental trajectories, it is difficult unless I know what the underlying model is. I don't know what really the force is. So and moreover, it also has this distribution, and computing distribution experimentally also requires a large number of trajectories, which experimentally might again be difficult. So implementing this formula experimentally is difficult, and in the last few years, people have come up with some indirect methods to estimate entropy production just from the trajectories without a priori knowledge about the underlying model. And these are like two examples. This one is by Supriya Krishnamurthy and others, where they use thermodynamic uncertainty relation to estimate the entropy production. And this is some other work by Edgar Roden, where they use the properties of waiting time distribution to make the estimation. But both of these methods work for steady-state systems. But we were interested in developing a method for time-dependent systems. And it turns out in literature, like there are relatively lesser number of works that deal with time-dependent systems, and these are two such works. But I'm going to focus on my work for today's talk. Okay, so our method gives a general bound on the total entropy production, mean of total entropy production in terms of the moments and the correlation functions. For example, if you have first two moments, the variance and the mean, then we can show that the entropy production is bounded in this way, where the sigma is the variance and x1 that you see is the mean. So now on the right hand side, we have everything that we can just measure from the trajectories. And if you give me, let's say 100 trajectories or so, I can just do the ensemble average and then get this quantities and put it here and then get an estimate about the entropy production. Next, I would now like to, I'm not going to go into the derivation of this, but rather I want to show like an application of this bound in a real experimental system, and it's about the heat erasure. So just one slide on what heat erasure is. So Landau in 1961, they showed that there's minimum amount of thermodynamic cost associated in carrying out some heat operation. For example, in the simple scenario where you have, say, 2 bits, 0 or 1 initially, and over the course of time, you do some operation such that eventually you just get 1 bit as an output. There's some minimal energy input that one has to give, and it's bounded by KB2 KBT log 2 in this way, where the equality holds in the quasi-static limit when you carry out this operation very, very slowly. In last 10 years or so, like people have within the stochastic thermodynamics community, people have tried to verify this bound, and a sketch of a typical experiment would look something like this. So you have a double well potential, and the particle can initially be on either side of the potential, and if it is on this side, it's like state 0. If it is on this side, it's like state 1. And state 1 and 0 are equally likely initially. And over the course of time, you change the shape of this potential in such a way that the particle always ends up in the one side of the potential. So you lower the barrier, you tilt the potential so that the particle eventually lands up on this side. And this is like the final output is just one, like it's state 1. So this is like a bit eraser operation where you are going from state 0 or 1 to state 1. And this is the potential that people have considered with the G functions, F functions are the experimental protocols that one can vary to carry out this operation. The typical trajectories would look something like this. So this gray trajectory you see here, the particles starts on the left side of the wave, and it does something in the middle, but it always goes and ends up on the right side. On the other hand, if it starts on the right side, it also does something in the middle, but eventually it stays on the right side. So these people here, they could carry out this operation experimentally, and they got some trajectories, and they used this definition for the work, where the form of the potential is given here. And then they looked at the average of this work experimentally, and I would like to bring your attention to this blue curve here. This is a work in the units of KBT as a function of cycle time. And they could show that as you go to higher and higher cycle times, the bound saturates to log 2. These are the experimental results, and but we were interested in verifying our bound with these experimental trajectories. So we took some number of trajectories, like of the order of 50 or so, and then we had this bound, so we had to measure the first moment and the second moment. And with this trajectory, we can do that, and we plug that here, and then we get the following estimate for the entropy production. So this is the entropy production versus cycle time. This green curve you see here are the results from simulation, because we know what the potential is, so we can simulate and get this mean entropy production. On the other hand, these red symbols that you see here are the estimate with this bound here. And I think I want to emphasize that we have considered of the order of 50 trajectories, and even with that less trajectory, it's quite close to the actual simulation results. This is another example, more theoretical, that we have looked at. We consider this very simple Brownian motion, free Brownian motion, but the initial distribution is chosen from this distribution. We chose the simple example because we could do calculations exactly. And again, here we see like the green, which is the estimate, is quite close to the red curve, which is the exact result. Okay, so to summarize my talk, we have derived a general bound on the mean total entropy production for time-dependent systems in terms of correlation functions and moments. We then apply this bound to infer the entropy production for weak eraser experiment, and we could see like the inferred entropy production is quite close to the actual simulation results. And as I said, one can extend this method to general number of points. I just focus on first moment, but one can fix any number of moments and get a bound. Moreover, one can also go to multi-particle settings and higher dimensional settings. That's there in our paper. And this is the reference, it's in archive. And I would like to acknowledge John Baker and Krishimaraj Kosha for helping us with the experiment today. Thank you so much.
Okay, let's take the time for a few questions. Yeah.
Basically, you need a first moment, second moment, and velocity.
Velocity.
And x dot of t.
That's the derivative of the moment.
That's the derivative of the moment.
Yeah.
So this can be defined even in non-thermodynamic systems. I mean,
Yeah, actually, yeah, this can be defined in non-thermodynamic systems. For
will it
example,
make sense to define entropy that way or
in
non-thermodynamic systems? That is some,
yeah, I think because the method that we use is taken from this optimal transfer theory, where it's like it's not thermodynamic. So in optimal transfer theory, what people do is, so you have some initial mass density, and you want to go to some final mass density, and what is the cost efficient way to do that? And in thermodynamic setting, the entropy is that cost, but I mean, there people have like different definitions of cost, like I mean, L2 something, I don't remember the name, but yeah, it is possible to give a non-thermodynamic interpretation.
Okay, so one more question here.
So in your equilibrium, the entropy production rate is 0, the total entropy production.
Yeah.
So can I see this in your bound? Does it come out obviously that your bound also gives 0?
If you are already at equilibrium.
Yeah. So I am in the equilibrium stationary state and I take trajectories
No.
there. There would be time reversal symmetry.
Yeah, yeah.
So the entropy production, the total entropy production is 0.
Yeah, no, we have, I mean, this particular thing gives you the bound when the system is relaxing to the equilibrium or to the steady state, but not like if you already start from the steady state or.
It doesn't apply there at the equilibrium stationary
No,
state?
because, yeah, no, it doesn't, because I don't know if I have that. But what we focus on is on this one-time property, and those are already constant in the equilibrium or in the steady state. So if you want to make a go to those scenarios, you have to look at I think two-time properties, which we haven't done.
Okay.
But the short answer is no.
Okay, we don't have any time to ask further questions. If you have any questions, please ask them direct. Let us thank the speaker. So our next speaker is one more.
I'm audible, right?
Yeah.
So good morning. Firstly, I'd like to thank the organizers for giving me the opportunity to present myself here. So today I'm going to talk about this relaxation and dynamic correlation in this hardcore uneven particles. So these two are the differences. So actually, in usually many body systems, characterization of transport is actually a problem of fundamental interest. But in diffusive systems, the transport coefficients they are related to the long-time statistical properties of currents in the following fashion. Like the diffusivity is related to the average current, like the usual Fick's law, and the mobility is somehow related. I mean, it's related to the long-term fluctuation. But this calculation of these two transport coefficients is actually a non-trivial task. Now, in recent years, these self-propelled particles have drawn much attention, and it has been reported that they exhibit actually a motility-induced phase separation, and the Meaves phenomenology actually suggests that or claims that the diffusivity or the bulk diffusion coefficient has an instability. It sort of vanishes at the critical point. However, there has not been, any rigorous derivation of this claim. But yeah, so this is actually phenomenologically changed. And in this direction, there have been some previous works in characterizing fluctuation and transport in various models of active particles. And these are the various models. And out of all these references, I would like to particularly mention this work by Rajesh, Damlekar, Saput, and Rajesh, where they have actually calculated these transport coefficients for a variant of uneven particles. Hardcore uneven particles, which is actually a directed mass transport model, and in the leading order of persistence rate. And also nowadays, actually, the velocity correlation. So it has been actually observed recently that even in motile active particles with repulsive interaction, the velocity correlation can become long range. So this velocity is closely related to the quantity called current. So that sort of motivated us to study a minimal model where we can study this fluctuation or correlation properties of currents, and whether we can relate them to these transport coefficients. So for that, we actually take a very minimal model like it's Raman thermal particle. So this is a hardcore Raman thermal particle. Each particle has some spin, and this spin sort of dictates the direction of motion. So we immediately the particle hops to the nearest site. So provided the destination site is vacant, and the spin flips or changes its direction with some rate which is gamma. This is called flipping rate. Now, this due to this extra spin variable, analytical studies in this particular model is found to be difficult. Moreover, it is to be noted that on the time scale of persistence time, that is 1 over gamma, a particle actually performs long range motion. So this sort of enables us to, so actually motivates us to introduce this model like long range lattice gas model, where actually these particles are hardcore, so they don't have any spin. So actually you are already get rid of this one spin variable, and particles symmetrically hop to any one of the direction. But the interesting thing is that they, while they hop, they perform long range motion, and this long range hopping actually is drawn from a distribution from phi L, any distribution. So now the dynamics is as follows: like particles are hardcore, so when it hops, so if the next particle is far apart compared to this L, then it will hop by length L. However, on the other case, if the next particle is much closer than L, then actually it cannot cross other particles. It will just jump and sit just behind the particle. So this is the dynamics, and although this model is non-trivial, but we can somehow manage this. This model can be analytically tractable. So we are interested in the quantity called time integrated current, like any current across any arbitrary point up to time t. So okay. So before going into the main details, so let me just summarize our main results. So we have calculated this diffusivity and mobility for any arbitrary parameter values. I mean, we have found that there exists a scaling regime in the limit of small density and strong persistence, and this is a scaling relation where rho over gamma is actually our scaling variable. And also we have shown that if you know this diffusivity and mobility, that is, these transport coefficients are known, you can in principle calculate this current fluctuation, and this current fluctuation also has a scaling limit in the limit of large time and large system size limit. And the next third result is actually this equal time correlation of current, but we have found that this equal time correlation actually is an exponential function, and the correlation length can become long range as we increase the persistence. So this is actually these are the main results. So yeah. Okay, so actually for this long range lattice gas model, we'll proceed analytically and verify our results numerically for RTPs. So in the next 2 slides, I will briefly give some flavor of our actual scheme. So you see, so when a particle, it's a long range model. So when a particle hops in a direction, so it will generate current across all the points in between. And for the rightward hopping, it's plus current, and leftward hopping is minus current. So you can actually consider all possible hopping events that generates or changes current in between at a time step like t to t plus dt. And then you can write down the time correlation equation, which sort of has this gradient property. So the system satisfies the gradient property. That means the current can be written as a gradient of some observable. But the observables are non-trivial because due to the long range motion, this observable they are multi-point correlated actually. So we can now perform this gradient expansion and calculate the diffusivity exactly in this model. And interestingly, that after some algebraic manipulation, we can relate this non-trivial correlated to the gap distribution of the system. So in that way, we can represent actually the diffusivity in terms of the gap distribution function. But after this, the scheme is exact. But the problem arises when you are asked to calculate 2-point correlation. So if you want to calculate the 2-point current correlation, this sort of has the time evaluation has this form, where the non-trivial term is the correlation here. It's like when this, because this correlation involves the correlation between this many-point correlator and time integrated current, and that not surprisingly not form closed structure. I think yesterday Shoikat also has talked about similar hierarchy of equations. So now in order to truncate, we actually propose a closure scheme where actually we have, I mean, motivated by the thing is that actually at last time when the system is in the steady state, we assume that actually the diffusive current operator could be related to the diffusion with diffusivity times the gradient of density operator. In a way, we are actually then actually equation 7 actually can be written as a density, some gradient of density current correlator, and under the approximation, this forms actually a closed structure. And so this is the only approximation that actually we have implemented, and that sort of enables us to calculate everything. So this is actually the analytical expression. These are the expressions like the diffusivity and mobility in terms of the gap distribution function, where the gap distribution function that depends on these parameter values. But for RTPs for which we don't have any analytical grip, so then actually implemented a numerical scheme like to calculate diffusivity. We actually study long wavelength perturbation, and the relaxation rate actually is related to the diffusivity, and one can perform them for any arbitrary values and estimate the transport coefficient. So you see that these transport coefficients, they are actually a function of density and tumbling rate. So each of these parameters, I mean, for length scale in the system. So there are two length scales. So one is this activity-induced length scale, persistence length, and another one is since particles are hardcore, so the interaction actually shows another length scale. This is a mean free path or gap. So this actually is 1 over rho times the particle cross section. So one can then immediately construct a dimensionless quantity, which is the ratio of these two scaling, these two length scales, and this is indeed the rho over gamma. So this actually explains the emergence of the scaling variable rho over gamma. And when actually psi tends to 0, that is the scaling variable tends to 0, here is a non-interacting limit, and when psi tends to infinity, here is a strongly interacting limit. And this is the scaling collapse. So you see that this is actually a scale diffusivity. It's plotted as a function of the scale variable, and these points are often from simulation, and this line is actually often from analytics, and we find a good matching. But the interesting thing is that in the strongly persistent or strongly interacting regime, so the diffusivity is linear in persistence rate, and it varies as x 1 over rho square. So that means there is no such instability that we have reported. So we haven't found any instability in diffusivity, and also this sort of observation is consistent with Rajesh's work, where for the mass transport model they have found that diffusivity is linear in persistence rate and independent of their density. So this, by suitable mapping, these two models are results are going consistent. Mobility, we have found similar results for mobility as well. So where this is actually the scaling function that we have calculated. So the last thing, so this is the bond current fluctuation. So you see, so we have shown that there exists actually another scaling regime for bond current fluctuation in the limit of large time, large system size, where we plotted this suitably scaled. So T and chi are the diffusivity and mobility. So we have scaled them suitably and plotted in terms of this scale time, dT over L square. And we found a good matching, and these points are from simulation. And this line is actually the scaling function that we have calculated. So this is the form of the scaling function. So it initially has this subdiffusive growth. It grows as root T, and then actually it crosses over to a diffusive growth. And these two regions, they are connected through this scaling function. And for RTPs, for which actually we didn't perform in analytics, but we found similar growth nature of current fluctuation, and in fact they actually superimpose on one another. So this is actually quite good. That means this current the scaling function is quite universal. So we have checked it also for another model, another various diffusive systems like for Statphys model and XCCP also. We find the same scaling function. And the last result is this spatial correlation of current. So actually we find that this spatial correlation of current equal time spatial correlation is exponential, and this correlation length is related to the parameter values in this fashion. And in the strong persistence limit, we find that effectively this correlation length diverges as 1 over square root gamma. But this sort of 1 over square root gamma actually divergence is, I'm almost done. So yeah, this actually has been reported in various studies in the context of velocity correlation, where they have found this length scale images from so there are a few references. This is, I think, the experimental paper, and yeah. So it's good that even for this minimal model, this length scale images. So okay, so I'm almost, yeah, I'm done. So these are the conclusions. Like we calculate this the transport coefficients at arbitrary the parameters, and in there is a scaling regime in the limit of low density and strong persistence, and we didn't find any instability. It is indifusivity. And also using a truncation scheme, we calculate with bond pair fluctuation, which initially grows the diffusivity and then makes a diffusive crossover. And the growth law actually satisfies the inverse scaling relation, and also the spatial correlation of current is exponential, and the correlation in divergence is 1%.
So let's thank the speaker. In time for short questions. Yeah.
So can you go back to the slide 18 where you like just one slide before, like the 3 papers that you have down there?
Yeah.
Well, the first one I'm not 100% sure, but like the last 2, like they do report velocity correlations, but without an actual particle current. It's like the particles are correlated at.
Oh, actually, they studied this. I mean, in experiment, it's easy to study the velocity. So they actually have studied this velocity correlation.
Yeah, in the experiments in the Henkes paper.
Right.
Yeah, but the theory which is there,
No,
it's on the instantaneous velocities
Right.
without that they consider displacements.
right.
Now, those velocity correlations, from my understanding, they emerge from forces.
Right.
Like you have the self-propulsion, and then you have
Right.
an actual force that is exerted from all the
Right.
steric interactions and so on.
Right.
Now, I don't really see the relation to the lattice models because you don't have forces there in the
Right.
sense that you say, let's say you have 3 particles on the right that want to go to the left with their self-propulsion force.
Yeah.
But you have 1 particle on the left that wants to go in the other direction.
Right.
This particle will block all the other particles on the other
Exactly.
side. Whereas in a continuum model, you would have more forces on
Yeah.
the right side, and they would be able to
Yeah.
push the particle in the other direction without that this cluster, which is wanting to move to the left, is blocked.
Yeah.
And this doesn't happen on the
Yeah.
lattice model. So I'm
Exactly.
not really
There
seeing
is some,
the.
yeah. I actually, there are some differences, but the interest. So actually, what you said is exactly right. So if you have more particles, they actually tend to push each other actually to this repulsive interaction. But here, you don't expect anything. But the thing is that, and that effect actually is, these two are actually distinguishable, and they are actually incorporated in the row dependence. So row dependence are different. So, but the thing is that the activity somehow actually manages to emerge the same length. But these two actually are different.
Okay, but so then when you look for the mechanism.
Yeah. No, they are in principle different, but it is related.
Maybe you can explain the relation to me later.
Yeah.
So there's no more time to take questions. So could you discuss during the break? Let's thank the speaker. Next speaker is Vishwajit Das.
First of all, thanks for the organizers for giving me the opportunity to talk about our work. So I will talk about some features of entropy current fluctuations in out of equilibrium system. So before going to out of equilibrium system, if we just look into a standard Brownian motion, we know the Brownian motion is a geo-mean Gaussian process. So the fluctuations have a first moment. So the mean of the fluctuation will be 0, and the variance of scales with t. And if we look at trajectory, and there are high probability of finding the trajectory up and down the average line. And long before, the Paul Levy showed that the time spent by a typical trajectory at any time over the average, okay, that time fraction actually distributed like this U-shaped distribution. So these are the time fraction if I consider, like those are the time fraction for which the trajectory is above the zero line. So they showed that this is a U type of distribution, and this distribution has a mean at 0.5. So and this type of distribution can be found from standard Brownian motion and any. Also, if you look at the cumulative distribution of the same time fraction, this can be followed like a arc sine type distribution. So that's why there comes this law or called arc sine law for the Brownian motion. So these kind of arc sine distribution have been seen in many other contexts like fluctuations of stock price, some leads in competitive sports, and in general, if a variable in binary process, you can say that there is a chance that the variable will follow the arc sine. And more importantly, Professor Sadhu later has generalized this arc sine law or even for fractional Brownian motion as well, where the generalized not only for the fractional time it's spent above the average, but also other two things that is denoted as T max, because this is the time fraction, the time fraction before this trajectory go to the maximum of its thing, and something called T last. So this is the time when the trajectory crosses this average for the last time. But these two things also they have shown that they are generalized arc sine law even for the fractional Brownian motion as well. Now, if we take a system out of equilibrium that Prashant had discussed a lot, so the system takes out of equilibrium by means of time-dependent driving or temperature difference. So then, in a recent work by this very they have shown that if we look at the current fluctuations, so we look at the time-integrated current like this, like the heat or work or entropy, they at the steady state distribution for this T plus with the fraction of time that fluctuations change above average, the steady state, they show this U-shaped type distribution. They proved it for generalized non-equilibrium system. Also conjecture that the two other time like this T max, this fraction of time trajectory spent until the current reaches its maximum distribution, and for the T last, they conjecture that they also will follow the similar. But this will happen at the steady state. Okay, so what we try to understand from here that what will happen at the short time. To understand what happens to this thermodynamic current fraction in the short time, we take a simple model which is analytically tractable as well as experimentally tractable. So that is, we trap a particle in, we basically consider a colloidal particle in a parabolic trap, and then to take the system out of equilibrium, we perturb the trap with exponential correlated noise with a finite correlation. And due to this external noise, the system will go out of equilibrium, and there will be a non-equilibrium steady state at the long time, and there will be steady state entropy production. And this parameter theta, by this parameter theta, we can say how far the system is from out of equilibrium, because the entropy production is directly proportional. Okay, so now what we looked at as the entropy current, the Prashant already discussed what is the entropy current. So for our system, we can analytically calculate the entropy current for all time. So this is basically the time intensive part and time extensive part, and this actually the boundary item which will go to zero if we take the steady state. But as Prashant discussed that if you have a trajectory of it can be experimental or can be numerical. From the actual getting this entropy current from the actual data, that can be difficult. So that's why we use the other indirect scheme based on the thermodynamic inference scheme, where this is a lower bound of the entropy production can be found in terms of the mean and variance of such current. And if we do a careful optimization, we can get actually the entropy production rate, and in this way we can get the actual entropy production current at any. So this protocol works this way. Suppose you have a trajectory, if you have a trajectory, you can construct some arbitrary current, with some function d, which is this is function of the trajectory. From there, this d is this function you can express in some basis, and if the current of the system is adequately expressed by a basis, you can do this optimization analytically, or you can do the optimization by some stochastic gradient descent algorithm. We did those things. So then, in this optimization procedure, you can get this coefficient, or if this current is maximized, you get the maximum entry production. And in this way, you can get the entry production current from from numerical data as well as from the experimental data. Okay. Now that we can have the entry production current from the data, but we looked at what happens at the short time to the variable t plus. So that is basically the fraction of time the trajectory spent average. And at steady state, it should show that U-shaped distribution which have a mean at 0.5. Okay. But what we see that if we see the current at the short time, this shows some non-monotonic dependence with time. So what we say at the very short time, this average is close to the 0.5. At the very long time, when the system reaches the state state. For the state state thing, that's also there is a 0.5. But in between, there is a non-monotonic thing, and this non-monotonicity actually increases if the system is more out of equilibrium. Because more the feature, the system is more out of equilibrium. Okay. And for the T max as well, we have seen the similar thing as well. So then we thought what could be the reason. So then we looked into the skewness of the current or the current. So what we find out that what the system we consider, the skewness can be analytically calculated. And this skewness also shows that at the very short time, the fluctuations are Gaussian, at very long time, the fluctuations are Gaussian, but in between, there is a non-zero skew, and there is a maximum skewness, and it actually increases with the system is more out of. Okay, so, and this can be understood from the asymptotic behavior of skewness of any current in the system. So, because it can be shown such current for t tends to 0, the moment like the mean and the square that it actually scales with t, but the cubic moments scales with t. So at the short time, the skewness scales with t to the power half, but at the long time, this scales with t to the power minus half. So to have in between, there has to be a maximum. Okay, so then we thought whether we can get this from the experiment as well. So we did the experiment with the optical tweezer setup. So basically, we trap a particle with a laser, and the laser is passed through something called Lacoste optic modulator through which this exponentially correlated noise is. So then we can have the trajectory and we can get the current. So to use a certain frequency and get the current to construct and then we check for the experimental data as well. The skewness show non-monotonic thing, and we show a maximum at certain time, and this maximum actually increases with the strength of the non-equilibrium. And similarly, the consequences like the teacher can be considered. Now, we for the linear one-time diffusive model, from the asymptotic behavior of the skewness, we can argue this thing is happening. But then we want to understand whether this thing is more general if we take a non-linear system as well. But to understand that, we take a overlap diffusive system which is non-linear. So we take for anharmonic Brownian jet, the details of this here. So what we looked at is that Brownian generator is basically if a Brownian particle is confined in a conservative potential, and along two axes like x and y, there are two different temperatures, and the two degree of freedom are coupled by means of some rotation or something. The system will go to out of it. Now, if the confinement potential is considered to be this anharmonic, what happens that the system still go to out of equilibrium, and we notice that this behavior of illness and the T plus and T max behavior is also there. So for the overlap diffusive system, this kind of behavior of skewness of the current is more general. And here also, this alpha parameter shows that how non-equilibrium system, those things what we have seen from the linear case can be seen here. And now our collaborator, theoretical collaborator, he looked at the Markov jump process theoretically. So basically, they consider a three-state process, 0, E1, E2, and there are some transitions, and Transitions from 0 to E1 is mediated by a temperature T1. Transition from 0 to E2 is mediated by T1, but transition from E1 to E2 is a different temperature, so the system will be in out of equilibrium. But in that case, it can be shown theoretically that for the T tends to 0 degree, the skewness is actually d to the power minus half. So here, that for this type of Markov jump process, this non-monotonicity is gone, and you expect the steady at the very short time. This has jump, and as we go the long time, this. So the what we can conclude that we have shown finite time skewness of current, but we should mention that this positivity of this quantity, like half minus theta, and this non-monotonicness or this thing with the relation of the skewness is actually like conjecture from numerical and experimental evidence, but this is not rigorously actually proved. So also whether this optimal time where the skewness peaks up has an importance in like in artificial engine or something that needs to be tested. Okay, so I need to acknowledge the other collaborators that are involved in this also. This is Monica. You are in Stanford, probably all the senior diploma by MS and Professor Surya Krishnamoorthy. Thank you. Thank you.
So let us thank the speaker, and we can have a couple of questions.
Did not show any plot for the U shape. How does it modify? Probably this you showed the skewness and moments, but whatever the full plot of the distribution, do you have any result?
So I'm not here, but we have a paper where we show for the steady state case that is like U-shaped properly. But if it is not in the steady state case, yeah, there will be deviation.
Is the deviation distorts the symmetry of the around 0.5? The symmetry of the distribution? Does it modify or does it change slightly?
No, the symmetry will also change.
Symmetry is also modified?
Yeah, because there will be some, the perfect U-shape will not be there. So there will be some kind of skewed jump and then drop like that. Some arbitrary.
Yes.
So the universality of arcs and laws for entropy production, is it true also for underdamped dynamics or discrete states or only?
So that different state, no, for the steady state it can be, but underdamped I am not sure. Because we have looked into the overdamped.
Only the overdamped.
Yeah. The overdamped and this Markov jump process, in a long time it will happen. This thing will happen, but the steady state case, it may not. I'm sorry, it was not like.
But for underdamped, it's not known.
Underdamped, I'm not sure.
So maybe a short question.
So even for any specific overdamped system, is it possible to prove analytically? Like,
so that's what I said. So that the TRL paper that Bharat, they have shown for that T max one. So basically the fraction of time, sorry, for the T plus only, for fraction of time it's above average. For that time only, that time fraction, they showed that this U-shaped distribution and they will follow the arc sign law. But other two things, this T max and the T last, they just conjecture. They also have not proved. And we also could not prove that this short time thing, there is a correlation with the skewness. We cannot prove it rigorously till now. We have just looked into the evidence that from there we are seeing. Especially for this type of system, numerically annular from the experimental data.
Okay, so let us thank the speaker.
Good morning, everyone. I'm Tripona. I would like to thank the speakers for giving me an opportunity to talk about my work here. So today I will be talking about statistical properties of particle symmetric system. To study the universal behavior in the spectral statistics of such system, I have used random matrix theory. So this is a 1D SSAs where the odd from the odd lattice point to the even the interaction strengths are denoted by alpha, whereas from the odd it's alpha prime. So if I write down the Hamiltonian in the side basis in matrix form, it will be a chiral symmetric one, or obviously the eigenvalues are symmetric around 0. So it's a sparse matrix and the dimensionality is 1. Now if we trace this 1D SSAs and arrange it in such a way to form a 2D lattice plate so that inside the placket the interaction strengths are same, which is alpha in this case, and outside the placket this is alpha prime. The Hamiltonian matrix is again chiral symmetry, but the sparsity reduced as the dimension increased. Now we incorporate the intra-sublattice interaction, but inside the placket only of the strength beta prime, and also incorporated on-site disorder for all the lattice points. Now it's no longer a chiral symmetric matrix. The diagonal blocks are non-zero now. Here I introduce the random matrix. I have considered the interaction strengths alpha, alpha prime, beta, beta prime to be Gaussian distributed random elements with different mean and variance. Now with different choice of the mean and variances, I have studied different properties of eigenvalue and eigenfunction statistics and found that both the spectral as well as the wave function statistics are very much dependent on these bond interactions. For example, for fixed alpha, alpha prime, beta prime, with increasing beta, the level departure increases and localization in the wave function also increases. Whereas for fixed alpha, alpha prime and beta prime, beta, with increasing beta prime, level departure increases, but the localization in the wave function decreases. And also the statistics depend on the sum and difference of this alpha and alpha prime. Now here we ask a question. Is it possible to formulate a single parameter which will have the information of all the mean and variances of these interaction strengths so that we don't need to really depend on individually with this alpha, alpha prime and beta, beta prime? And if possible, then the statistics based on this single parameter will show any universal behavior for different combination of this alpha, alpha prime, beta, beta prime. Now we generalize this problem to particle to a random matrix system. For that, we have considered a particle symmetric system with time reversal and speed rotation symmetry, but the matrix elements of the Hamiltonian are random and taken from Gaussian distribution. The mean and variance of the distribution can vary. Now, let me explain these constants in the context of random matrix theory. So, the conditions which influence the nature of the random matrix ensembles are called constants. The system-specific information like symmetries, conservations, log, which merely determine the structure of the Hamiltonian matrix are called matrix constants, whereas other type of constants are called ensemble constants, which declares the local relations among the matrix elements, for example, distribution properties like disorder. So here in our system, I have fixed the matrix constants, but the ensemble constants can vary. Now with different choice of these ensemble constants, different ensembles can be achieved with fixed matrix constants. Now the matrix elements of these ensembles are multi-parametric Gaussian distributed. So again, we ask we can go back to our questions in a general form that is it possible to form a single parameter which will have the information of all the ensemble parameters? And if possible, then we be the statistics based on that single parameter which show universal behavior for different ensembles. Now, before answering this question, let me show you how the Hamiltonian matrix with particle symmetry look like. So this is a CI class of particle symmetric matrix where the diagonal and up-diagonal blocks are individually symmetric. CI class means along with particle symmetry, there are two other symmetries. Now, the elements of these block matrices are Gaussian distributed random numbers. So if I write down the joint probability distribution function of our ensemble, it will obviously have all the distribution parameter, that is mean and variances of all the matrix elements. Now, with different choice of this distribution, choice of the form of this distribution parameter, one can achieve different ensemble with particular symmetry. Now, our question was, is it possible to form a single parameter so that we don't need to worry about all the distribution parameters separately? The answer is yes. By studying the parametric evolution of that ensemble density, it was possible to formulate a single parameter, which is named as ensemble complexity parameter, which is basically an average logarithmic function of all the ensemble parameters. I'm not going into the detail of the calculation, but here you can see it is not only dependent on the distribution parameters, but also dependent on the system size. This complexity parameter was first introduced by Pragya Shukla in the year 2000, where she studied complex Hermitian matrices. Later, for different class of random matrix ensemble like orthogonal, unitary, and symplectic ensembles, this complexity parameter formulation and universal statistic based on this parameter were studied. For chiral symmetric ensembles, I have studied with Pragya this complexity parameter formulation and spectral statistics based on this parameter. Now, this is the complexity parameter of particle symmetric ensembles of CI class. Now, to study this numerically, it is required to rescale this complexity parameter with local information of eigenvalue and eigenfunction statistics. Since both the statistics are very much dependent on the energy range we are considering, therefore it was necessary. This local information comes through this local mean level spacing. So here you can see that our rescale complexity parameter is not only dependent on the ensemble parameters, but also very much dependent on the energy range of interest. Now for the block diagonals, now for the block matrices of our Hamiltonian, I've considered different ensembles separately. These different ensembles were considered with different choice of the variances, and to reduce complexity in our calculation, I've taken all the mean of the distribution for all the matrix elements to be equal to 0. And I picked the other elements so that this variance is dependent only one parameter. For example, it's in Brownian, the variance is dependent on C, in Anderson it is dependent on W, and its exponential ensemble is dependent on this P. Now I calculated this rescale complexity parameter for different ensembles at different energy range with several values of the variances. And here we predict if the numerical value of this rescale complexity parameter lambda is same, the statistics will follow on the same graph. Now for eigenvalue statistics, I studied this property called nearest neighbor spacing ratio distribution, which is defined like this, where R is the ratio between consecutive spacing. And this is the result. Here you can see that as long as the value of lambda is fixed, though the ensembles are different, the energy ranges are different, the distribution curve, all of them are overlapping with each other. So here we can say that it was possible to formulate a single parameter and the spacing ratio distribution at a fixed lambda will show universal statistics for different ensembles. Here, another property one can see that when the lambda value is higher, the statistics is going towards the Wigner-Teichel direction, whereas for low value of lambda, it is towards the Poisson direction. Here we try to find out how the statistics changes with the at each point of lambda. For that, I have taken this local average of this nearest neighbor spacing ratio, and here you can see this average spacing ratio is very much sensitive to the energy range of interest, and it is different for different ensembles, and for different variances it's also different. Now, if I plot this average spacing ratio with respect to lambda, here we can again see this universal behavior and the transitions from near Poisson to the GOE limit. One can see, and this average spacing ratio is proportional to the logarithmic value of our complexity parameter with a fixed transition rate. So the take-home message is here. Take-home message here is that it is possible to formulate a single parameter for a particular symmetric system, and the statistics based on that parameter will show universal behavior for different ensembles. Now, I studied the set for interpolating ensembles between chiral and the particle symmetric system. I'm not going into the detail of this, but what I can see that at different instances of this interpolating ensemble, the similar behavior we have found. Now let's go back to our 2D SSH model, where all the interaction strings are taken from Gaussian distributed, taken as Gaussian distributed random numbers. Here also we have calculated this lambda, which is the scale complexity parameter for this 2D SSH model. And then for statistics, I studied this average spacing ratio. And here also we have seen this average spacing ratio is proportional to logarithmic value of this complexity parameter with the same transition rate. And also this transition is universal, and Poisson to zero transition is again found for different choice of this variance and mean. So I can summarize my results here. So first I have considered a particle symmetric system of CI class. Then I calculated the complexity parameter, which is basically a combination, a function of all the ensemble parameters. I incorporated the local information of the statistics in that complexity parameter. Then the block matrices of the Hamiltonian are taken from different ensembles separately. And for spectral statistics, I studied the ratio of nearest neighbor spacing, and I have found a universal behavior in the statistics for different ensembles. And also for average spacing ratio, we have found that this property is logarithmically dependent on our complexity parameter with the same transition rate. I have found the same for interpolating ensembles, and for 2D SSH model also I got similar results. And for further details, something we can. Thank you for listening.
Okay, so I'm just speaking on time for questions. Yeah.
Can there be a simpler parameter? Because the only odd man out is alpha plus alpha prime, where the level repulsion goes down. The rest of them have similar effect on the quantity. This is what I thought.
No, they are not similar. They are not similar. The localization also decreases.
Yeah, only this particular.
I mean, this is for the eigenfunction property. This is eigenvalues properties. I mean, I have only incorporated only one thing here. So I have studied different statistics, and they are very much dependent on what value we are choosing and what combination we are using here. So for that, it was our interest to find out a single parameter.
Yeah, I thought so, because there is only one down arrow in this table.
And this is also very complicated. That's why I have not written here. So it is not directly dependent on, I mean, I cannot say that when the alpha minus alpha prime increases, the level repulsion increases or decreases. So at bulk, its behavior is different, at age, its behavior is different. So it was necessary to study these parameters.
Yeah. So when you say that interaction strength, you mean bond strength or usual density interaction? Bond strength, right? Now, why do you need to study SSH chain? You can have a tight binding model in a square lattice that will also have particle symmetry.
That anything can be done. So we started from SSH, and that is why we generalize our results to a particle symmetric system.
And because in your result you don't even include the fact you have a topology or not in the system.
No. Topology is not studied here. We are actually generalize the system for particle symmetric one, and I studied that.
Right. And your choice of alpha beta, does it in the topological phase or in trivial phase?
I mean,
the mean value of alpha beta in the random distribution.
Okay, so the topology I have not considered here. So in the trivial space, where I mean, always alpha prime is greater than alpha.
All right. Okay. Thanks.
Yeah.
Okay, maybe one more question.
I have just a query, like in your last slide. Could you please? Slide 5, like this one. Slide number 5. Okay, yeah. So you have shown that the level function is higher and the wave function localization is getting there. So far I know that you have a system with disorder and you are trying to get the localization. So the level function should be minimum at that localization part.
Yeah, but
that's as you are going from GOE to POE, right? Okay, so 0.29, it has to be level
I
function.
understand your point that when it is delocalized, the functions are delocalized, eigenvalues should have, I mean, less level departure. So that is what you are saying.
Yes.
But we did not found it here.
It's on the process.
No, we did not found that thing here, that direct correlation here. That for uncorrelated eigenvalues, the eigen functions are delocalized, so that is not. I mean, for the correlated eigenvalues, the eigenfunctions are delocalized. That is not here. We have found here. So this is what we have found for increasing beta prime, because beta prime is on-site disorder here. So it's not that. I mean, all the other parameters are 0, so they have the significance. So when the level departure increases, it's not that eigenfunction localization also increases. It shows the delocalized behavior when I studied the inverse participation ratio and all. but the level requires some increase. So it's ambiguity there.
Okay, I think we have to close the session. Let us thank the speaker again. So we reassemble here at 11:40 as a tea break. And the speakers for the next session, please upload your talk during the break. Oh, no. Okay.
we end of title if we push the after title push 1/8 for at the same time, it's very আমরা অলমোস্ট ব্যাচমেন্ট মানে আমরা একসঙ্গে পড়ি পরে আলাপ মানে ওর পড়লেও আমার এবার ব্যাপারটা হচ্ছে যে মুহূর্তে আমি স্ক্রিন থেকে ক্লিক করছি ওই মুহূর্তে আমি ওয়াকারটাকে ডাক দিই বা বাংলাটা করার আগে স্ক্রিন তার করেসপন্ডিং সিলেক্ট করা তারপর সে বাদিকে যেতে থাকছে ওভারঅল যখন আপডেট মানে সঙ্গে সঙ্গে স্টেপের মধ্যে র্যান্ডম আপডেট মানে তাতে হতেই পারে যে একজন একই টাইমের মধ্যে দুবার ডাক দিচ্ছে আর দুবার বাক দিচ্ছে হতেই পারে আবার এমনও হতে পারে যে একবার ডাক দিতে পারবে আমরা তিন জায়গায় কারণ সময়টা তো আপ ডাউন হতেই পারে দুবার আপডেট হওয়ার পরে খুবই কম এই একটা কনফিগারেশন তাহলে পারবে
একটা পার্টিকুলার প্রত্যেককে আলাদা করে র্যান্ডম আপডেট দেখছো যদি তুমি ওইটা আপডেট অন্যরকম করে করো তাহলে চেঞ্জ
হ্যাঁ ওরা তো হচ্ছে আবার এখন তো ওমিক্রনের ভ্যারিয়েন্ট গুলো আসছে কতটা সিরিয়াস বোঝা যাচ্ছে না টেকনোলজি
সবাই থাকছো তোমরা প্রথম কবে যাবে একটু যাবে না ওই তো 9, 14, 19 সেমিফাইনাল হলে 24 ফাইনাল ফাইনাল হচ্ছে রবিবার 28 তারিখ কি না মানে এই থেকে তো একটা টিম বলতে পারে ছাড়া আগে পারবে না তোমরা সবাই সবাই যারা যাবে ফাইনাল জন্য আমাকে কালকে তোমরা ফাইনাল নিজেরা কথা বলে যে যদি মনে করো যে না না তারপরে 9 তারিখ মঙ্গলবার 14 তারিখ আমার রবিবার রাত্রে সেটা আবার রবিবার যাওয়া যায় আমার যে কোনো ঠিক আছে খাওয়া দাওয়া
So we start the next session. Paranguma.
Okay, hello everyone. Let me begin by thanking the organizers. So the Statphys Kolkata conference started more than 30 years back, and from a very small conference, it has now become a big event. So, and I have the honor of being associated with this almost all the Statphys Kolkata meetings. But after the first one or the second one, when it started to become bigger, it was decided that the organizers cannot be speakers. So after a long time, I had this opportunity to speak in a Statphys Kolkata meeting. So when I got the invitation from Mumbai, I immediately jumped and said, yes, of course I will be here. I will be happy to talk here. Okay, so let me begin the talk. So we have these are the collaborators. Actually, Reshmi, Pratik, and Shoham, they were all graduate students when these works were done. And now Reshmi is a postdoc in IMSC. Pratik, you already heard yesterday, is faculty here. And Shoham is also a faculty in Mexico. And Purushottama, I think you all know, is in IMSC. These works have been supported by ACR. So, very brief introduction to interactive particle systems. We take systems in which there are particles and we update the position of the particles at each time. And time can be discrete or continuous. And we define some general rules of update. The update will involve some kind of stochasticity, and usually we take Markov rules. So, the specific types of systems which I consider are reaction repeating systems, which are very popular systems and important in very kind of multidisciplinary, important in many fields. And essentially, you have this kind of a reaction. We also constituent materials or reactants which react to give some output products and with certain assigned rates. And the end result is often some atomic pattern formation. Okay. So what we'll talk about today, I'll talk about is single species case, which means we have only A type of particles, and in general a reaction can be like this: A type of particles meet and they undergo a reaction. After that, L type particles are left in the system, and K less than L means there is some annihilation. The simplest case possible is, of course, two particles coming together, annihilating, so that we are left with zero particles. The most important issue usually in these systems is how the concentration of the species are influenced by the motion of the reactants. And if we take a perfectly homogeneous system and mean field kind of treatment, then this del rho del T can be written as this. And if the reactants, as I said, it is a homogeneous system, then the first term can be ignored. So at long times, we are left with this kind of a variation in the density of particles. But of course, true asymptotic behavior will depend on the dimension. So let me define the model which I am going to consider here. So we have a plus A going to 0. This was actually considered started long back, that we started talking about this. And the particles can hop to the nearest neighbors, but the hopping probability is dependent on the position of the neighboring particles. So in this case, you see they try to go towards their nearest neighbor with a bias. So you have 0.5 plus epsilon bias because this particle is nearer compared to this particle. So the probability to hop towards this particle is more in an attractive dynamics. And that is why I have used the words dynamic bias, because you can see that this bias is going to change in time. Whoever happens to be the nearest neighbor, that will dictate the direction of motion of the particles. And because there is annihilation, this direction can change. Because your nearest neighbor may die, so you have then you're left with a new nearest neighbor. Okay. And in case the two particles, the two nearest neighbors are at the same distance, then you can just move to either with same probability, equal probability. So one can ask me that why this model at all? So let me tell you that there are some limiting values of epsilon which are very well known and important. So one is epsilon equal to 0, which is a purely diffusive case. And this corresponds to zero temperature Ising-Glauber model in one dimension, which was realized long time back. And almost all results are available there. On the other hand, if you take epsilon equal to 0.5, but the bias is kind of deterministic, that the particle will always go towards its nearest neighbor, then one can also have a one-to-one correspondence with the model at t equal to 0 once again, where the size of the neighboring domains determine the time evolution. Yes?
So in this case, Walker also dies when he sees the neighbor.
Right. Both of them die. If they go to the same site, or if there's already, if the site is already occupied, then both of them will die.
Then you have a new Walker in the system.
No, I'm not generating Walkers. No, ultimately everyone will die.
And the reaction process is deterministic, or it's also
reaction happens with probability 1. Okay. So this was a spin model which was actually proposed even earlier, and in this spin model, I'm not going into the details of this because of lack of time. If you are interested, we can discuss that later. So let me just show you some snapshots as we vary epsilon. So this is the diffusive case. Then here we have epsilon equal to 0.1, 0.3, and 0.5. You can see the trajectories. They become very different as soon as I introduce an epsilon, because you see the number of particles are much less as they move towards the nearest neighbor. And in case of the extreme bias, you can see that the paths have become almost ballistic. So starting from diffusive, we can have a journey from a diffusive to a ballistic kind of motion. So,
but for epsilon equal to half, one of the direction is
always not in the picture. Right. Okay. So what are the quantities of interest? First of all, the usual bulk properties I already mentioned about the particle decay in time, how rho depends on time. Then there is also persistence probability. Here persistence probability is defined as a fraction of unvisited sites. And in many cases, we know that it decays in a Paolo manner with a new exponent. New in the sense that this exponent theta is not related to any equilibrium or non-equilibrium exponent that we know. So for the limiting values, again, let me tell you what are the results. These are not exact results. Eta is half and theta is 3/8. But when epsilon is not equal to 0, then from simulations we find that both eta and theta are independent of epsilon, and eta takes the value 1 and theta takes this value. So this defines a completely new universality class as far as dynamics is concerned, are concerned. So then we move over to another important feature, which is the interparticle distance distribution. So if Nk is the number of intervals, we have been hearing about these gaps. So it's the same thing, number of intervals of size k in a system of size L. Remember, this is a one-dimensional system, and we can define Pk equal to Nk by L. Then sum over Pk will represent the total number of interfaces, and this Kpk acts as a probability and sums to 1. And the average k is nothing but 1/2. Okay, so if I get this thing, then I expect to get eta also, as well as this full distribution is interesting to know. Now it is expected that PKT will follow this kind of scaling relation. And let me now tell you what were our results using for this PK. So to get PK, what we did was we used the independent interval approximation where you can write down a master equation for Pk, and it comprises of two terms. One is independent of epsilon, so it is essentially for the diffusive case when epsilon equal to 0. And when you introduce epsilon, then you have this additional term. The first term is well known, and the second term looks kind of horrible. I'm not going to explain all these terms here, but the thing is that when you only have this first term, you can solve this equation by hand. But when the second term enters the picture, all you can do is solve this numerically. So doing that, we found that, let me just tell you what happens for epsilon equal to 0, because results are known there and one can compare. So IIA gives correct result form, that is this scaling function is exponential. Also, it gives the correct value of eta equal to half, but the exact exponential decay is not given. What I mean is, if it is e to the power minus alpha x, the exact result gives 1 alpha, but IIA gives a different alpha. But qualitatively, the results are correct as far as the scaling function is concerned, and eta is given correct. So let us see what happens when we have epsilon not equal to 0. Then using IIA, we can obtain eta. Sorry, the notation was different in this paper. So what is Z here is nothing but 1 by eta. And we saw that for two different values of epsilon, one small and one large, we get Z very close to 1. So this is an additional evidence that Z eta will be very close to 1. And we also find that the scaling function is exponential even when epsilon is equal to 0. Now let me compare this with the simulation results. In the simulations, we also found the similar kind of result. There is exponential decay, and Z is almost 1, which means eta is also almost equal to 1. And as we got in for epsilon equal to 0, here also we find that this alpha is different from the IIA result in case of the simulations, and it's not surprising because already we have seen that for epsilon equal to 0 they do not match. So here also they do not match. Okay. So later on, there was a paper by Parth who proposed a general form of this model, introducing more parameters, and in one limit you can go to this model, and then he also used the approximation approach, not the IIA but a different approach. Also, additional approximations were required because exact result is not possible to get here, and it was found that eta is equal to 1. So this is just a supporting paper. Okay. So next thing was that once we knew the bulk properties, we were interested to see what happens at the microscopic level, how the individual particles are moving in the system. Why do we ask this question? See, when eta is equal to 1, it means that essentially it is a one-dimensional system. So the distance traveled is of the order of t, which means a ballistic motion. But we know that the walkers individually are not ballistic because they have this bias is not always 0.5. If it is less than 0.5, then the diffusive component will also be functional. So for any epsilon, still we get the same result. So we try to probe that if there is something happening at the microscopic level, which can tell me that which can tell me that there is some dependence of certain quantities on epsilon or not. So what we studied here is the probability distribution. That is the usual thing, the probability of finding a particle A at distance x from its starting point. Then st is the probability of direction change at any time, and d tau is the distribution of the interval of time tau spent with the change direction, that is with how long they are traveling in the same direction. Once again, for epsilon equal to 0, we know the motion is purely diffusive, and this probability distribution is Gaussian, scaling variable is x by t to the power half, etc. So for epsilon not equal to 0, we found that pi xt changes completely, and it has a double peak structure with a minimum at the origin. Now let me show you the data here. This is for the early time regime, and this is for the long time regime, and we find that here the scaling variable is x by epsilon t. So once again, this is a check that x goes as t, and we also see how epsilon enters into the picture. In fact, in the IIA study also we got this indication that epsilon enters the picture in this form. Okay, so when we scale by epsilon, then these curves they fall on each other. But you can see that at the long times, it is not so good. The collapse is not so good. And we proposed a form like this, which has a nice agreement for the early times, but at the later stages, the agreement is not so good. And we conjecture that if we go to even larger times, this will actually become a double delta function. The problem is that the particles die so fast that it is not easy to analyze the behavior over the entire time range. So early time, it's nice, you can get all these things, but you can see the scatter in the data because data becomes very scarce because most of the particles have already died. Yes.
Why is it greater than 1?
Which one?
The peak positions on the right. Other plot.
It's here?
Right plot.
Right plot?
The value at which its peak is greater than 1.
No, it's not greater than 1. 7.8.
No, not that. X-axis.
X-axis? Yes.
So you think that these particles that escape.
Oh, this peaks. Okay, so basically what happens, you have both, ultimately there will be both right moving and left moving particles. Okay, so there will be, the ballistic motion suggests that. And here we see that there is an equal, it's symmetric, so there's equal probability of having right moving and left moving.
Yeah, but it's not actually centered about the peak.
Okay. So,
yeah, what are beta and gamma? Are they fitting parameters?
no, there's no relation to critical, they're just parameters. And you would expect by this form that they will be time independent, but there is a very weak time dependence in one of the parameters. I forgot which one. But anyway, I should not emphasize on this form a lot because this is just a guess, kind of. It's a guess from the distribution of Ising spins when they are continuous. The probability distribution looks like this. From there, we thought that it can have a correspondence. Okay, but here you see that the first evidence of epsilon equal to 0.5 and epsilon not equal to 0.5, some difference is there. That there is some difference. That evidence comes from this quantity, which is the probability of direction change. Of course, for epsilon equal to 0, when things are completely unbiased, you have the probability of direction change equal to half. Here you see that for 0.5, it is actually power law. It is going as T inverse. But for the rest of the epsilon values, it becomes a constant after some time. Of course, that constant is less than 0.5. So it behaves like a biased one, but not in this manner, not a time dependence. Time dependence is lost. Okay. Now we can do scaling from this also and try to collapse the data when epsilon is very close to 0.5, and we find that there is a collapse like this, and the scaling function behaves like this, that it is almost a constant here, which gives you the T inverse kind of behavior. But at later times, you see that this is linear, almost linear, it's 0.95, which shows that it will be time independent. How do we interpret this result? We say that there is a crossover which is happening at T star. You know T star, of course, this is just a repetition. It behaves like T inverse, and where T star ST saturates. So we interpret this as that as when T is less than T star, particle density is still large, and annihilation plays the key role in determining the dynamics of the particles. But for T less than T star, annihilations become rare, and then the diffusive component becomes dominant, and therefore you see something similar to the epsilon equal to 0 case, although there is still a bias. It's not half, it's less than half the probability of direction change. Now, next we also studied the time interval spent between consecutive change in direction, and this ignore one of this because we took another model for this similar behavior. Also, collapses found very similar behavior. There is a scaling function which is nearly a constant in the early region, and then it becomes it shows a different behavior. And you can see that we can also associate a time scale here, and even for the earlier case, and this time scale varies as epsilon c minus epsilon -1. So we say that this epsilon c acts as a dynamic critical point, and this divergence is associated with that critical point. Okay, ignore the rest. Fine. Now for epsilon equal to 0.5, some analytical estimates can be made about this exponent, because at epsilon equal to 0.5, the only way it can change direction is when an annihilation takes place. So we just take that into account and assume this form that the number of particles go as T inverse. Then using some very simple argument, we can show that HT goes as T inverse. Similarly for DT also, one can show that it goes as T to the power tau to the power -2. Okay. Now I introduce you to another kind of the dynamics which I was discussing till now involve asynchronous updating. Asynchronous means that you take the time as continuous, and therefore you update the spins immediately after a change is made. For the parallel, it's different, and with a simple example, we'll tell you why they are taking it synchronous. In this case, this is asynchronous. So you see that when this particle P2, it makes a move here because it's the nearest neighbor, they will both be killed. But in this case, what happens, you don't update, in parallel update, you don't update them immediately. You update them together after all the movements have been made. So when P2 goes to P3, they are not killed because you still assume for P3, P2 is still here. And P3 makes a move here because P3 considers P2 to be the nearest neighbor. So essentially what happens is their positions are swapped. And also there are lots of evidence in literature that asynchronous and parallel will give you different results. Okay, so this still do the same kind of things which I'm not going into detail. The rho is like this. There's a log p factor now entered here. But what is interesting is we see a new phenomena which is a dimerization. Because the particles can swap positions like this, you can see this structure here where two particles are going on swapping their positions. So we also did these things, but I think that Rajesh is looking at me threateningly. So because of lack of time, I will move more to the two-dimensional problem. Okay, but before that, let me also tell you that till now we have considered only attractive dynamics, but there can be repulsive dynamics as well. So for repulsive dynamics, you can see that this is for again mod epsilon small and mod epsilon large. This is the maximum repulsion case. You can see the structure is very different. The particles will decay in time, but it will be very, very slow. Okay. And in fact, we did find that, but I'm not going into the details because I want to discuss the next problem, which was the same work studied in 2 dimensions. Now, in 2 dimensions, things become a bit non-trivial because in 1 dimension, you can define your nearest neighbors and go towards that and so on very easily. But for 2 dimensions, you have 4 nearest neighbors. So there can be different dynamics which can be considered. We considered 2 cases, but I'm going to discuss only one. The case I'm going to discuss is that with probability epsilon, the particle will go to a site which brings it closer to its nearest neighbor. Otherwise, it goes to any other remaining neighboring site. Okay, and epsilon, a little difference between the there. In the earlier case, epsilon was from 0 to 0.5. Now we have epsilon from 0 to 1. Epsilon equal to 0.25 is the diffusive point because you have 4 directions, so equal probability to go is the diffusive case. On the other hand, epsilon equal to 0 is the extreme positive bias case, and epsilon equal to 0 is the extreme negative bias case. Some results were already known since a long time for epsilon equal to 0.25. The particle density with asynchronous dynamics analytically was found to be of this form. For parallel dynamics, we couldn't find any reference, so we did it ourselves, and we found numerically that it is of the same form with A almost equal to B. The values are different if the dynamics is different. Now, there is a general case. We will consider the particle decay, and here we did the parallel dynamics only, and for some computational convenience, and we found the dimers are present here also. Let me just first summarize the result. We found an interesting thing. And epsilon is valid. Look at this figure. we find that up to 0.25, there is a non-zero number of particles left in the system. Then you cross epsilon 0.25, then you find a non-zero number of diamonds. And then we claim that there is a phase transition happening at 0.25. In order to support our claim, we did a detailed analysis of the data, and we found some scaling relations like rho t. Then we used the known form for this. In the scaling relation, you can find that there is a time scale defined by epsilon c minus epsilon. Epsilon c is 0.25. And from the other data, that is, if we look at the rho value obtained at the maximum value of time simulated, it shows an interesting feature. It becomes flat after epsilon exceeds a certain value. For different length scales, it is different, but then you can collapse the data on a single curve, and it is found that this also obeys scaling. Again, from here you can define a length scale which goes as epsilon c minus epsilon minus 1. We claim that this is the correlation exponent mu. We also see cross-check this by looking at the epsilon c is of course size dependent. So we find that this relation is obeyed like in a continuous phase transition. So from here we also estimated a mu, which turned out to be equal to 1.13, which is close to 1. Similarly, we cross-check for the dynamic exponent, which from the diverging time scale, we found to be going like this with A1 equal to this. And for cross-checking, we used finite cell scaling analysis using the different length scales, and we saw that this 2 and 2.1, they agree very well. Okay, and so as I told you, the dimers will have non-zero value, and they also show a scaling. This is like this. And I will end with this, that there have been numerous works done after this, and presently we are looking at a problem in which we have some walkers which are rigid but not hooked at all. So I have already exceeded my time. These are concluding remarks. Thank you once again for the work.
So, good to write down the phase diagram. This is the last problem you talked about is 2 dimension, right?
2 dimension, right?
And how is it possible that the particles, some particles remain, like they will collide at some point?
Okay, particles can remain for several reasons. Okay, so it depends. It's a discrete lattice, so it depends on the positions also. So if even suppose you have it may not be possible for the particles to merge at one point. Can you use the board? So suppose you have a particle here and a particle here. It may never be possible for the particle to come here and here and hit each other. That can happen. I don't know whether this is a correct diagram, but something like this happens because the discreteness will not permit it.
In one case, you get 1 over t, and in another case, in one case, it's a drift and diffusion, right?
Yes.
Or, so, can you interpolate between these two limits by getting it proportional to length, rather length square, or length to half, or some power?
Puruda are doing something like this at present. They are looking at that problem.
Is there a continuum limit analog of this problem? For example, epsilon equal to 0 case, is it the Fisher's random Brownian motion problem?
I have not thought about the continuous case.
The reason I'm asking is because there you can write down the many particle properties. So any of these results of tracer and others, probably they could be tractable.
I don't think about it. Right now, I don't. I have not done it. As far as I know, nobody else has done.
The annihilation rate should also be an important parameter in design phase diagram, right? So, have you done anything like that?
No. We thought we look at the simplest thing with the minimum number of parameters. Now we are increasing parameters, like I told you, that we have some rigid walkers and so on. So that can always be done. And this guy Park, he has 2 papers on the same thing. He has also introduced branching and all. So a lot of things can be done. It's kind of an open problem. If you want, you can do.
Any other questions?
I have just one
Hello?
comment to
No,
make,
no.
which I, for
Let me
shortage
ask
of
one
time.
question.
Okay, please.
So this two-way going to 5, it was faster. But if you do 3A going to 5, it is fast. 3A going to
Okay, right, 3 particles.
then you can have timers forming and then they can be at very slow paces coming.
Right, okay, maybe.
But the 3 of them have to come together.
So I thought I would make a one small comment during the talk. That is, you will see that the two-dimensional paper, the paper on the two-dimensional wall, is published in 2019, whereas the one-dimensional is in 2020. The reason is, I remember Parvika gave a talk about the waiting time. So the waiting time for referees' comments is also an interesting question. And for 2050 it was too long.
Yes, thanks for the comment. Next talk is by Olivia Manu.
Hello everyone, I am Adhya Monika, PhD student at the Department of Physics, Presidency University, Kolkata. Today I will be discussing about effects of random field on critical behaviors of anisotropic XY ferromagnet in 3 dimensions. XY model introduces a unique characteristic, the ability of spin to rotate in a plane. This is different from Ising model, in which spin can have just 2 directions. In XY model, spin can point in any direction, introduce a additional degrees of freedom. This introduces SO2 symmetry. The Hamiltonian of such system can be written by this equation. Right? J is the nearest neighbor ferromagnetic interaction strength. SI is the unit length 2D spin vector, and theta corresponds to the angle of the spin at the ith side. The XY model exhibits SO2 symmetry, implying that its behavior remains unchanged under continuous rotation in 2D plane. This symmetry arises due to the ability of spin to freely rotate. In Hamiltonian, the cosine terms encapsulate this symmetry. You can see that it remains invariant under rotations. These are the examples of XY model. It exhibits interesting phases in 2 dimensions. BKT transition, where unbinding of vortices disrupts the continuous symmetry, resulting in a phase transition without having long-range orders. Topological phases. Superfluid helium, thin film, superconductivity are great example of XY model. But these were the cases for isotropic system. Now let's have a twist. Instead of absolute rotational freedom, giving the spin a preferred alignment direction. In literature, it is termed as anisotropic. You can say that in Hamiltonian, the anisotropy is taken in such a way that if gamma is equal to 0, it will map to the conventional XY model. If gamma is equal to 1, it will map to the XX model, still retaining the continuous symmetry. Anisotropy influences the way spin collectively arrange and how they respond to the external factors like temperature, magnetic field, which we'll see when we proceed further. We have employed Monte Carlo simulation technique to understand the behavior of anisotropic XY ferromagnet in 3 dimensions. It is worth mentioning that the spin dimension is 2, but the lattice dimension is 3. A simple cubic lattice of L is equal to 20 is considered, and periodic boundary conditions are applied in all 3 directions. From these 2 figures, you can get an idea about the orientation of spin depending on the value of anisotropy. If gamma is positive, the spin orientation dominates over along the x-axis. For gamma negative, the spins prefer to along the vertical direction. So anisotropy can stabilize the spin configuration and break the SO2 symmetry. Understanding the effect of anisotropy, we have studied the phase transition in anisotropic XY ferromagnet in 3 dimensions. The thermodynamic phase transition in a ferromagnetic system is generally studied by the thermal variation of magnetization. The magnetization vanishes at the critical point, and the susceptibility diverges at the critical point. However, for a finite size system, the critical temperature is determined from the point where the susceptibility gets its maximum. We are considering a scenario where anisotropy is uniform across all spins. It means each spin experiences a same degree of directional bias regardless of its position within the system. As we started to cool the system from a high temperature random state, magnetization grows and it's found to saturate to unity. The thermal variation of susceptibility determines the critical temperature by showing the peak. So there exists a conventional para to ferro phase transition in 3D anisotropic ferromagnet if there is a long range order below the critical temperature, which was absent in case of isotropic XY system in 3 dimensions. In 2 dimensions.
Is there anything like Binder-Equivalent which you measured?
Yes. We have research. From Binder-Equivalent, we calculated the exact TC.
You didn't show that.
No. From this figure, you can see that the susceptibility peak shifts towards right with the increasing value of anisotropy. The critical temperature increases with the anisotropy strength. This figure shows a variation of critical temperature with the anisotropy strength. The critical temperature is found to increase linearly with the anisotropy strength. From the straight line peak, we can estimate the value of Tc at gamma is equal to 0, which is in good agreement with the isotropic XY model Tc in 3 dimensions, that is 2.206. Moreover, for gamma is equal to 1, the system maps to XX model. The Tc for the gamma is equal to 1 is very much closer to that of MC's estimate of 3D Ising ferromagnet, that is 4.511. Now let us incorporate a uniform random field to the system. Mathematically, the Hamiltonian takes this form where initial is the applied uniform random field. The randomness of the field is governed by its angle phi I. Phi can be varied from 0 to 2 pi uniformly with constant magnitude A. Note that there is no long range order for 2 and 3 dimensional isotropic XY system in presence of field. From literature, we came to know that the lower critical dimension for having long range order in case of isotropic XY system with random field is 3.9. Let's see what happens for anisotropic case. As we cool the system in a similar fashion, magnetization grows. In alliance, magnetization grows. The susceptibility exhibits distinct peak from where we can obtain the critical temperature for the finite size system. From this figure, you can see that the susceptibility peak shifts towards left with the increasing value of field strength for fixed value of anisotropy. This figure shows the variation of critical temperature with the random field strength. For a fixed value of anisotropy, the critical temperature monotonically decreases with the increasing field strength. So the random field acts like a quench random disorder and reduces the TC of the system. From the first part, we have seen that the constant anisotropy breaks the SO2 symmetry of the system, favoring the spin orientation over others, and the critical temperature increases with the constant anisotropy strength. On the other hand, the random field disrupts the spin orientation and introduces a disorder to the system that reduces the TC. So the interplay between the constant anisotropy and random field is a fascinating competition. The question is there any random field value which can compensate the rise of TC due to the presence of anisotropy, or which can preserve the isotropic system TC? Yes, if we can carefully adjust these two factors and finally tune, then the critical temperature of the we can get the critical temperature of the 3-dimensional isotropic XY ferromagnet. We have computed several critical temperatures for several values of field strength and several anisotropic strength, and by interpolating them, we get the compensating field, the field required to get the TC of isotropic system, that is the 2.206 for this case. Here we have plotted the pair of compensating field and the constant anisotropic strength and fitted to a straight line. This straight line corresponds to the TC of T equals to 2.206. That's the TC of isotropic XY model in 3 dimensions. Any thermodynamic behavior or phase transition is generally formalized by finite size analysis. We have done the finite size analysis for both case, constant anisotropic case and with the field case. Here I have shown the result for the using the random field strength. The phase transition is supported by the growth of critical correlations. Here we have plotted the thermal variation of susceptibility and specific heat for different system size for a fixed value of anisotropic strength and random field. You can see that the susceptibility shows a divergence in the critical point. Estimating the scaling laws, we can obtain the critical exponent for this. These are different from the isotropic XY ferromagnet as well as the anisotropic XY ferromagnet without having any field. Now let's summarize all this. There exists a long-range order even in 3 dimensions in terms of anisotropic XY system. The directional preference imposed by the constant anisotropy can be cranked down by applying a random field with full circular symmetry, and the compensating field, that is the prescribed amount of field which retains the critical temperature of the isotropic XY system, was found to depend linearly on the strength of anisotropy. And the scaling exponent claimed that the random field anisotropic XY ferromagnet belongs to different universality class than the usual anisotropic XY ferromagnet as well as the isotropic XY ferromagnet. These exponents are different for the 3 different cases. With random field, it is 1.46. In isotropic system without field, it is 1.96, and for anisotropic system, it is 1.752. These are the references. And I would like to thank my supervisor, Professor Mukti Shasarji, for his guidance and my funding agency. And I would like to thank the organizer for giving me this opportunity to present my work here. And thank you for your kind attention.
Isotropic XY model in 3D with a finite field. We have a transition. Homogeneous finite field.
In 3D.
Yes. So do you have a phase diagram in HD plane? Just for isotropic.
The critical exponents which you obtain, do they satisfy, have you checked, they satisfy the scaling relations?
Yes. Yes. From this case, we have not the good data of field accumulation, but for anisotropic system without field, we have the data of good data of field accumulation. From that, we get the TC and the scaling exponent also.
I also noted that you took a 2-dimensional field, right? You showed 2 components.
Yes.
So when you did 3-dimensional, you studied the problem in 3 dimensions. No, the field was still 2-dimensional.
Field is 2-dimensional. Field is circularly symmetric. Okay. With constant magnitude 8, the phi can be varied uniformly from 0 to 1.
No, that I am. Thank you.
So did you try to look at the nature of transition, the order of phase transitions for the system without the random scale?
Now we
the anisotropic model.
Yes.
So did you try to look at the order of phase transition, first order, second order, or something like that?
Now we are trying to do this with elliptically polarized field, and we are trying to guess the order of transition in that case.
Mm-hmm. But with the random field, you tried to look at the order, right? And there, because you showed the critical exponents. Yeah. So that means you have looked into the order transition, right?
These are the second order phase transition.
The second order. And in presence of magnet, the anisotropic case, it is
Second order?
Second order.
Okay. And with field, what happens? It should not be second order, right? It can be first, should be first order, if at all.
With random field.
With a field, the anisotropy model with the field, magnetic field, right? It should be first order.
The equilibrium transition we have. So the field is not time dependent. With constant field, till now we have seen the second order transition.
I see. And the finite effect, how big is the system that data price?
For finite size, last we have taken L is equal to 30 Q.
30 Q. You didn't do then block analysis, right? I mean, because that sort of, with exponent in a more less.
Let's thank the speaker for one answer.
If you have extreme case, gamma equal to 1, then with constant field it will be first order, isn't it? I think with homogeneous field will be first order, isn't it? Yeah, gamma equal to 1 case.
We have not tried for gamma is equal to 1.
Also, if you change the randomness, the exponent change 1.46. I mean, strength of randomness. If you change the strength
1.2 value, right?
These values, do they change if you continue to change the strength of randomness continuously?
So it's
Are they independent of the strength of randomness?
independent.
They're independent.
That could be only for very low density, right?
I think we can, lot of questions we can discuss later, maybe. Thank you. The next speaker is Rinki Sabnot.
Hello everyone. To begin with, I'd like to thank the organizer for giving me an opportunity to present my work in this conference. So, title of my talk is truly digitized feature model, and what is not published yet. So, any comment and suggestion will be appreciated. So, before going into the details of the models and results, computational results, let's briefly talk about the collective motion. So, we know that collective motion can be clearly seen in active matter system, which consists active particles consume energy to cell copper, and active system also shows various spectacular collective behaviors like Hawking transition. So we can see from nature that from macro scale Bartok to peaceful to micro scales, microbacterial clusters. Now, this collective emergence is also called the Hawking transition, and the first theoretical work in this line of research was done by Dietrich. The simple Dietrich actually took the simple alignment rule, position and theta update. Via these two dynamical loops, they have shown, Dietrich shown that this Hawking transition can be also seen as a order to desire transition, like ferromagnetic to like Tera to ferro transition. And where eta plays the same role, or noise plays the same role as the temperature. However, later or at the same time, turn into some hydrodynamic description of the Dietrich model, and at the zero velocity limit, the Dietrich model actually mimics the two-dimensional X-Y model. Now it takes almost 2 decades to almost 1 decade to prove actually Dietrich transition is actually first order transition. Previously it was thought that it was a second order. Now later Solon and their at all come up with a discretized version of the Dietrich model. Most simple discretized version was active Ising model, and where they have shown that with decreasing the noise, we are suddenly come from a disordered gas phase to a coexistence regime, where in Richard regime, we see a number of bands called the microphase separation, and in the active Ising model, the microphase separation actually transform into a macrophase separation. So now people actually very recently try to bridge these two model. Actually, one DR model and one is the most simple discretized version. And to bridge between these two models, people actually come up with the active clock model. Thing can take any discrete orientation depending upon how Q is, and the model actually there is a bias distribution, and also the spin not only can fit in the next hour. So only, let's say this is the spin, so this spin can fit only this orientation and this orientation. And via this model, they have actually shown that for a small q, they have shown the macrophase separation like active Ising model, and also as q is increased, we are going to the picture limit. So we are getting the microphase separation in the coexistence range. But the simple phases are gas. Only the three phases are there: gas phase and coexistence regime, macrophase, and the liquid phase. Now, here comes our motivation of the work. We are defining a model which not only discretize or try to bridge between the two models, and also follow the simple feature rule. That means, so here is the motivation that the dynamical rule is inspired from the feature model, and we ask the question: what happens then the collective behaviors of the dynamical phases? And these are the questions we ask in the model, that if number fluctuation can explain the macrophase or microphase condition, or and the ordered or the liquid order or polar order state, so the nature of the polar order state in the decide. So the model is very simple. Let's say I am an agent, so I look at my neighbor within the interaction radius and take the average orientation of my neighbor. Now, during that process, I make a mistake, so I get a new orientation, which is the blue angle, which is actually same as the checked orientation. However, due to the discretized version, this angle may not be possible, so or may not be allowed. So it will actually fall any two of the neighbors orientation, that depending on the probability. So how close it actually if it is close to the any existing, then probability will increase. And this simple projection rules, or the simple dynamical rules inspired from the reject, we have seen a spectacular 6 different collective phases from. Okay, so we know that for very small noises, and in the feature model, in small noises, we see a polar order liquid state, that is also called the corner 2 phase. But here we have seen the small q, the liquid phase actually converts to a cluster like this. The cluster cannot actually continuously grow to make a homogeneous liquid phase, because when the noise is small and also the orientation is few orientation as possible, then those cluster cannot actually coherently merge with another cluster to get bigger and make a ordered liquid state. However, if you increase q, that means I am allowing the particles to self-propel or in a mode orientation, or the degrees of freedom is now increased. So
right, let's say eta equal to 0.4, 1, 2, in the second column, 1, 2, 3, 4,
yeah,
4 and 5. 3, 4 with respect to 5.
This is
no next picture. Next, so this is horizontal, right?
This is actually vertical.
And it could have been horizontal also.
Right.
So what's the difference between this one and the other one at q equal to 8?
At q equal to 8. Okay, so q equal to 8. These are actually dynamical phases. So at steady state, this should have I mean, let me come to the point. So if we increase the q, we allow particles to self-propel in more volume to get homogeneous liquid. However, this also can be done by increasing the noise. So on the cluster phase, by increasing the noise, we are actually increasing the fluctuation in the system. So now the cluster phase has to actually merge together and make a single band in small Q unit, which is called macro phase. However, if we increase Q, then this macro phase actually transform into a micro phase separation. But as you asked, that for typical day, this is look like a macro phase, but actually here this should be a micro phase, right? So this is not actually steady state. Actually, I need more runtime to get a micro phase here. So,
What is the x-axis and what is the y?
so this is the iterative plane. So Q is the orientation, and y-axis is noise.
In the pictures,
Oh, picture. This is a square lattice, not lattice, operating person. So 2D is operating. So in simulation we get, but here also we have seen a cross like this. So this is in the coexistence regime, but cross is different from microphase because this cross actually can be observed only when two opposite or two different kind of bands collapse from opposite to each other. Then this like picture can be seen. And now when we increase the noise, then we see the disordered dashes. So to distinguish between the different phases, we have the magnetization order parameter, but this cannot be actually useful when we measure measure the order disorder transition, because order disorder transition can be seen by magnetization order parameter. However, this structure cannot be distinguished via this magnetization order parameter. So we define a structural order parameter called C2, which actually measures the overlap area between the particles. So when two particles very close to each other, the overlap area will increase, and which will give the C2 value very high. So to distinguish that, that's the cluster phase. Then for liquid and gaseous phase, this is homogeneous phase. So that's why the value of C2 is less. However, in the coexistence regime, the order of the chronology of the C2 is macrophase. For macrophase, it is larger than cross phase, and for microphase, it is less than macrophase. So via this C2, we have defined, we have actually distinguished this and actually draw a phase diagram. This is not shown here, but in the iterative plane, we have drawn the phase diagram. And the number fluctuation, as the number fluctuation, we have explained that while macrophase and microphase is actually seen by increasing the Q. So actually, when Q is increasing, the system number fluctuation actually increasing. So this is a close to a giant number fluctuation, and the macrophase actually breaks down the number of microphase that we see. And next, we have also seen the PDVM or the discrete model ordered liquid phases nature. So we know that check model actually shows the long range order. It survives the spin wave fluctuation, which actually cannot be put by the Martin maximum. So breakdown of Martin maximum in the non-nuclear scenario. So in that case, we have seen that when Q is increasing, the long range order or the value of the magnetization order parameter does not decrease. It is constant, and it also increased. So that means when I'm approaching to the Bichek limit, that is Q can swing anything, we actually reproduce that Bichek-like feature. However, when velocity is zero, that means the Bichek model convert to a two-dimensional expand model. Then the correlation falls, or the magnetization order parameter falls, and it is called the quasi-long range order phase. Now, this is the last slide of my result. So before going into the details of the, let me explain first that previously it was thought that the order or the polar order phase is very much stable in the Bichek model. But recently, work done by Odin et al. In 2022, where they have shown this polar order phase actually in the Bichek model can be reversed, or the orientation, global orientation can be reversed by a small perturbation in the ordered liquid. So we have also seen that in our discretized version, we have placed here, like small counter propagating droplet. So this order flow is actually moving in y direction, and the small droplet of opposite orientation is moving in the right direction. And then we have seen this droplet actually growing and make a curve-like band, and these counter propagating bands convert this homogeneous order liquid phase into a reversal order. So the orientation actually totally opposite to each other. So that means that the fraction of product space is also metastable in against a small perturbation. So in summary, you can see that macroscopic details or the dynamic roles in the plotting model can be give a very different result or the macroscopic behavior of the order. Also, we can conclude that the polar order liquid phase is susceptible to counter propagating droplet, signifying the optical metastability in the discretized version of the Hitching model. So, thank you. Let me thank my supervisor, Professor Rajapal. This is present in the audience, and my collaborator, Professor Igor from Salan University, and Shanoji Chatterjee also is a postdoc in the lab. Also, he will be part of this work. Also, thank my funding agency CSI and Foundation of Science. Thank you.
Any questions?
These domains which are forming, have you noted how they are forming the time dependence?
Actually, in steady state, we have actually analyzed the cluster size analysis for domain. So for only for Q equal to 4, we have seen that with noise, the cluster size actually increases, but suddenly it drops and makes the order.
Yeah, but the exact time dependence you have.
So no, time dependence I have not measured.
So how do you define the clusters? You're still saying cluster size, right? So how do you define the cluster?
So cluster size, so cluster actually defined by the polarity of the cluster. So each cluster is different polarity. I mean, they take a different orientation. So via the orientation, we have defined this is the cluster. This is another cluster. So in the snapshot, I have not shown this via this angular orientation. The snapshot is only the density of the particles, so that's why it's looking like all the clusters are same, but they are different polarity.
Yes. So these stripes, do they propagate? I mean,
yes, they propagate along to the orientation.
Okay, so this black stripe here dynamical in nature. Okay.
Let's thank the speaker one more time. The last speaker before lunch, Sandeep.
Okay. Let me start by thanking the organizers here for giving this platform. So my talk will be on diffusion dynamics and persistent probability of an active asymmetric Brownian particle in 2 dimensions. So I'm from Raman Research Institute, and this talk is based on these 2 papers, one is published and another is an archive. So let me start by defining some background, which is first passage and persistent. So let me talk about first passage. So let us let us take a particle moving in plane, let's say, or any one-dimensional thing, and we set a reference point or an absorbing wall at some point. Let's say at x0, x is equal to 0. So we track the particle, and the particle is moving in the time evolution. And at some point of time, the particle touches the absorbing wall, and it gets vanished. So the probability that touching the wall for the first time is called basically first passage probability. And conversely, if we say that the
probability sustaining of the particle before touching that wall is called basically persistence probability. So if there is no wall and we take a reference point, let's say x is equal to 0, which we have used here, and we take the particle evolution in time frame, and we track the particle evolution, and particle starts getting evolution, and moves around, and it starts touching the x is equal to 0, crosses x is equal to 0, comes to the negative direction, and again one persists in negative direction. So this persistence means that it persists beyond this x is equal to 0 for the probability that it persists for longer time. So basically the relation between the first passage probability and the persistence probability is this, which is basically first passage probability derivative of the persistence probability with a minus sign, because it is like if you increase persistence probability, the first passage probability will decrease, and so on, and the converse of the thing. So okay, so few important results, which is the simplest. This is the simplest Markov process, which is taken in this reference. So I have shown here. This is Mojumdar and Tripudichar and Alan. So this is the simplest Markov process. We have seen that the exact expression is this, and for the longer time limit, it goes to like 2 to the power minus half decade, where this theta is the exponent, persistent exponent, which is half. And this is the simplest non-Markov process, which is random acceleration. In that case, it is theta 1/4. And for higher order processes, these are for 3, n is equal to 3, n is equal to 4, and n is equal to 5. These are the quantity. The fact is, this is numerically found results. The analytical results are yet to found, so it is of course a problem. So my model is this. The particle is ellipsoid, and it has, it has different diffusion coefficient along both the axes. One is in major axis, and another is in minor axis. So this particle has a propulsion velocity along the major axis. This you can say v0, and this has a, let's say, an external force, and this external force has some component along this lap frame, fx and fy, and this fx and fy component has some projection along this body frame, which is this quantity. So this particle has the dynamics, let's say, two dynamics. One is translational dynamics, another is rotational dynamics. When the translational dynamics influenced by this v0 and the noise, and of course when potential will be there is the influence of potential as well. And for this rotational dynamics, theta involved, that depends on also this noise, and in the presence of any external force, there will be a torque generated because of the external force. So this is the Langevin equation in the body frame. If you see this, these are the force components, and if you take this, and you will find this Langevin equation in the body frame, and you will see that this gamma x and gamma y are basically this mobilities along this major and minor axis, and gamma theta is the mobility along this rotational axis. This theta is torque generated because of this external force. So we have said that this is basically the diffusion coefficients along parallel and perpendicular axis, and these are mean zero mean and respect correlated noise. So now if we transform the body frame to lap frame, we use this transformation relation, and we find that the previous Langevin equation evolved in this way, and we will find that the previous Langevin equation was uncoupled along B parallel, B perpendicular, but here it gets coupled, and this coupled turns out like this gamma bar, which is here, and delta gamma, which is here, and these are just like this gamma bar is the average of two
to mobilities, and delta gamma is the basically asymmetry constant, asymmetry parameter, which has been here very influencing parameter. So there will be a transform fluctuation relations as well, and which depends on this mobility tensor basically. So this gamma ij transforms in this form, and these are the references for the spherical particle. So I will show here the results for the asymmetric particle. So this is the for free case where fx and fy will be 0 and x and t evolution will be in this formulation, and we find that this mean square displacement along x-axis and y-axis with exact formulation, and these are the exact formulation and with analytical calculations, and we find from this relation, if we put delta d 0, which is basically asymmetry parameter, you will find this the exact value of the mean square displacement for the isotropic particle. So these are the simulation results. So in this result, you can find that there are two time regimes basically. One is the digita where t less than digita inverse, and another when t greater than digita inverse. And when t less than digita inverse, there will be two regimes we found. One the instantaneous t regime where this MSDs are dependent on t, and thereafter followed by this super diffusive regime with t square dependent, and in longer time after digita inverse, you will find this again diffusive, and this becomes 2D effective, where D effective turns out to be dependent on Q0, which is propulsion velocity. So these are different choices for d theta, which is the rotational distribution coefficient. And we find that for the small time regime, if we approximate up to second order, for very small time, you can see that this t term will dominate for this one, and for a little bit time evolution, you will get this t square dominance. So if the initial angle is changed, in the previous case, initial angle was 0. And if the initial angle is changed and it becomes pi by 2, you will see that for increasing V0 propulsion velocity, you will find that this is more super diffusive. So these are the diffusion coefficient. You will find that in the instantaneous regimes, these are acts like anisotropic particle. In the later regime, it goes isotropic. So the particle in harmonic charge is basically a non-Markov process, and we use to solve this process which is close to Markov process by using this perturbative expansion method, where this asymmetry term and this stiffness coefficient term will consist the perturbative expansion term, and it will give this. So it is the general equation just for this. So when we expand this for weak asymmetry and weak confinement, so we get this equation for the perturbative equation, and we form this new zeroth order, first order, and second order forms of this particle, and we find that this for two time correlation, equal time correlation, we find this correlation matrix which depends on 0, 0 star, 0, 1 star, and so on. For the sake of complications of higher order terms, this 0 and 1 star is calculating for this star will get horrible mathematics and calculation. So we have calculated up to first order, and this second order has we have from second order we have reflected the terms. So after this calculations, we find this exact expression of MSD from this perturbative expansion method, and we find this from this expression. If we take this kappa tends to 0, which is basically the case for free particle, we find the exact expression of MSD from this expression. We find the simulation results for different d theta, and these are for different stiffness coefficient values, and these are for different propulsion velocity values. We'll find that this after a time it goes like it attains steady state, and these are the trajectories for free particle, and this increasing kappa with the stiffness coefficient, and increasing stronger the confinement and stronger the earlier the steady state is achieved and more localized form we can find. So the persistence probability, to calculate the persistence probability, we have to take a route to find out from non-stationary to we find out two-time correlation. So to the non-stationary two-time correlation function, we can map it into stationary correlation function by some transformation, and after mapping into a stationary correlator, we use this Slippian form that it's a longer time for stationary Gaussian process, that persistence is proportional to the two-time correlator. We use this formulation and find out this persistence probability. So this is the two-time correlation for P particle. We have taken a small approximation here where T1 greater than T2, and for this approximation we have taken only because this formulation is stationary, and when it is stationary, it is hard to get the persistence form. So we take this approximation to neglect this term, this T1 minus T2 term, so that we can find out a non-stationary process. And we also show we have shown that whether this process is Gaussian. We have calculated this non-Gaussian parameter, and we found that in the longer time regime, the non-Gaussian parameter is past e to the power minus 1 decade, e to the power minus 1. So it is it is a Gaussian process in the longer time. So now we take this transformation of the two-time correlation, this transformation to find out this stationary non-stationary to stationary process, and we define the spatial transformation and temporal transformation, and after this transformation we find out that the new transformed correlation becomes exponentially decaying, and whenever it is exponentially decaying, we follow this Slippian theorem to find out that this is exactly equal to the correlation for the persistence exactly equal to the correlation. So these are the simulation results. You will find that for the longer greater V0, in shorter time limit, the theoretical results are, of course, in approximation it doesn't so much matches well, but in the longer time regime it goes constant. It follows the expression. So we find that in longer time regime it follows like isotropic particle because it goes constant, and Pt goes to e to the power minus half 1. So this is the results I will show for the harmonic trap. So harmonic trap, we have earlier shown this correlation matrix. We have calculated this correlation matrix. Yeah, last two slides. So we have calculated this two-time correlation matrix, and this is very much complicated mathematics. And we find out that two-time correlation function, which is exponentially decaying. So here is the effective trap constant, which changes because of this propulsion velocity and this asymmetry factor. And this is the exact approximated form of persistence probability, and these are the simulated results for that. For this is for kappa, smaller greater kappa and smaller kappa. We'll find that it exponentially decays for higher kappa. So this is the summary. Okay. So thank you.
The last slide is probability exclusion.
No, this is for this one, right? Pt e to the power minus kappa. So that goes to this. That is.
So firstly, then there's that is the last talk of the session. Shabita, any comments? We come back here after the fourth session. That's both the what you worked on.
Advertising competition. When this one is dominated, the other one is dominated. To have a singularity. It's not necessary. The third one will not come into this. Why? So it's possible that the diverse model. Sometimes. Always fine. Let a new one come in. So it's not dynamics, not this.
This PDF file is really transfer. How can I transfer an email? Yeah, I could have been there. I can. I need a, and then do it is a, that's a black blue. So, oh, this is really works. Engines, last. Not right? Yes. Let's see. It's coming up.
How are you? Yeah, so good to see you. So surely not at all put the vote. So but it's the same. It's a same. Yeah. Yeah.
জায়গায় যদি ও ব্যবস্থা করতে পারে আশেপাশে প্রবলেম সহজ আমাদের ক্যাম্পাসটা এত ছোট যে ওই মাস্টার্স থিসিস স্টুডেন্ট না মানে অফিসিয়াল যে ওটা ছাড়া
Yeah, it's like Julia, like Romeo and Juliet. Yeah, and then the yeah, yeah.
I came yesterday and just here.
Don't worry. I want to see for 5 minutes.
তাহলে আমি ওর সাথে কথা বলতে পারি কিরকম কতটা সময় স্পেন্ড
Okay, then welcome to the last session of this conference. We will have 2 talks, and the first speaker is Ushoshi Roy, and she will talk about emerging spatiotemporal multistability enabled by the biomechanical underpinning of different gene regulatory network motifs.
Thanks, Julian, for the introduction, and my sincere thanks to the organizers for giving me this opportunity. So I'll talk about spatiotemporal multistability by different gene regulated networks. So let's see what is this. So let me just tell you what is multistability in this context. So for this, I have 2 illustrative examples. I'll start with, this is a pictorial depiction of Weddington's epigenetic landscape during stem cell differentiation. So this is a ball rolling downhill. The valleys correspond to different stable states. So this ball can stay in those stable states, and that correspond to different differentiated cell states. This is another example from epithelial to mesenchymal transition states during cancer metastasis. So these are again the states, different states of those cells. Let's see how we can track these things mathematically. So multistability allows genetically identical cells to exist in numerous molecularly distinct and mitotically stable states. So let me start with the paradigm of my talk today. So all of you know that biomolecules interact, they give cell level behavior. Different cells interact and we get a tissue level behavior. Tissues form organs and organs form organisms and so forth. But this is not just a nested structure, but we should remember these 3 points, that each layer has problem-solving capacities in their own space, how activities in one layer is affecting the other, and how interactions at different levels is giving rise to some emergent biological phenomena. So this will be the paradigm of my talk today. I'll have, in that kind of scale, I'll have gene regulatory network motifs. Then this is a similar mathematical framework where I'll just consider diffusive mechanism of intercellular interaction, and then we'll see spatiotemporal patterning. So what a gene regulatory network is. This is as complex as this picture, with thousands and thousands of genes interacting with each other. These are the nodes and the edges by which. So like, I think the only way to characterize these things might be AI and ML, but let's see. Let's break it down. And Urialan and his group identified that these kind of complex structures are made up of small set of recurring regulation patterns called network motifs. And these network motifs, they can be found in different organisms from bacteria to humans, suggesting that they serve as the basic building blocks of transcription network. So what can be a simple, this is an archetype of gene regulatory network and is called a synthetic toggle switch. So A and B represents two genes or two transcription factors, and they repress each other. So these are mutually repressing genes. And let's say what kind of phenomena these give. So this shows bistability. I'll go to how it gives bistability and all. This is an example of branching morphogenesis where you can see like bistability means it gives two cell fates. And these are some of the examples of ACT's different length scales from blood vessels, lungs to neurons. And here is a cell fate mammalian tree where each, like every point, every branch point, they give two branches, right? And those two branches has two cell fates. So these all are illustrative examples, what we can get, what we might get from a toggle switch. So these are the governing equations, and the scripted H here in the first term is called the shifted Hill function. And how we can represent that shifted Hill function in this way, where in general we might write it down in the like as a combination of activation and repression. And the different parameters, if we tune those different parameters, different kind of behavior emerge. What kind of behavior emerges? So these are like time plots, and here what we have varied is kind of A. So what we see for some parameter regimes, there is only one monostable set, only one monostable solution. Even if we start from different initial conditions, we end up in one cell fate. But for the same stem mathematical equation for a different parameter set, we end up in a bistable regime, which is shown by this red part are the two stable coexistent gene expression levels states, and the 1 and 3 are the two monostable states. So let's see if we can integrate space into this. Why? Because spatial organization in biology is very important. And I'll just quote Cross and Brindside. What they said is perhaps the most magical moment in a pattern forming system is when a pattern first appears out of nothing. And by nothing, I mean some spatially uniform system. So as we all know that biological systems are exceedingly complex, nonlinear, out of equilibrium. So let's look at a simple mathematical framework. And for that, I'll take Alan Turing's famous formalism of reaction diffusion system. So this is a brilliant idea. So you take two stable things, reaction and diffusion. We all know that diffusion of one species is a stabilizing process. And by reaction, I mean you have A, you have B, and you slam it together and you get a stable reaction. But when you have both the things together, you have diffusion-induced instability. But remember, this multi-stability-driven spatiotemporal pattern, these are quite different from what Alan Turing referred to as these Turing patterns, and he got these patterns during morphogenesis and in activated substrate systems. So what we do, like I was telling you about this toggle switch thing. We have like diffusive molecules, and we have a 1D chain of cells, kind of this. We embed this network inside one cell, and the molecules of these can diffuse across the cell, across the chain. So what do I mean by that? The meaning is we have a local reaction, and the reaction is form of this genetic toggle switch, but the molecules can diffuse across the scale. So in those kind of things, like I already told you about this reaction part. Now we just included a diffusion. And in 1D, what do we see as time evolves? We can see for some part of the time we have these bistable things emerging, cells emerging from this system, and then again going to a monostable state. What happens when we have a 2D sheet like this? So what is this? This is a crude way of saying that this is a biological membrane, a monolayer of cells. And in this, we again embed a toggle switch and see what, and diffusive molecules around. So what do we see? As time progresses, we see these patches. The meaning of these patches are, so yellow and blue represent two different gene expression levels, and they spontaneously emerge, they side by side. This yellow and blue refers to two different gene expression levels of that system. So yeah, this is like a tug of war mechanism going on between A and B, which is giving rise to these kind of patches. And these are kind of quasi-stationary in limit, like what I was telling, like with time, as time progresses, the change of the shape of these patches change, and we see kind of different things occurring at different time points. So I'll go to a different scenario now, which is kind of omnipotent in any cell, and you consider this as a cell, and there are some protein here. And these protein can auto-regulate itself. And we have, like, if the cell grows, anyway, the protein concentration will go down. So we'll have this dilution process, and this, like the cell is growing. So we have a two-step negative feedback, and which is acting as an effective positive feedback. And then, because of this two positive feedback, we have, and when we embed this kind of just omnipotent scenario inside a cell, and we see what kind of tissue level behavior this system is giving, what we see is an emergent bistability. And and we have seen, just you take away those two loops, and what you just end up in pure noise. So this bistability is just arising out of these two negative feedback parts.
So the toggle switch is sitting in each box?
Yeah, in the previous scenario. And now we have a different motif like this. So we just see like kind of different toggle switch. Those toggle switches are talking to each other via a diffusive mechanism. But the reaction is like at that point, it's very local within the cell. So this is another scenario. So that was a toggle switch. Let's see, so you have seen, right, the genetic network was pretty complex. So now what we consider is a coupled toggle switches. I'll go to realistic biological network and you will see different things. So here are three toggle switches interacting with each other. And this is called a toggle triad. And similar way, we embed this in a 2D tissue. So and, I'll give you an example from a biological, like this is kind of a motivation, and you see this is the network which is behind patterning of the vertebrate neural tube, and you can see these three are forming a toggle triad. So with some extra interactions here. So this is capable of producing this pattern. So mathematically, we want to study what this is producing and whether what we see from a simplistic mathematical reaction diffusion mechanism. Let's see. So what we see, we can generate all this monostable, bistable, and tristable, these three states, and like for for some parameter region, this same system gives monostability, for others bistability, and also the tristable regimes. So we got a third state from these three interacting components. So this is just, we are within that bistable regime, and we are playing around with the diffusion coefficient. Playing around with diffusion coefficient means, actually, since it's the ratio of the spatial and temporal time scales, so we are kind of varying that, right? And by doing that, we can have different patch size and different cells at different gene expression states. So they are being capable of doing different works, right, at different diffusion coefficient. So those kind of scenario we can get by just tuning in the diffusion constant there. And this is also like we are in the tristable regime, and we get similar kind of phenomena where we increase the diffusion constant and we get different patches. So what do I mean by these states for a toggle triad? I just explicitly have shown it here. This is this is a three-component system, and these all are 8 possible monostable states for such a system, where you can see that two extremes are when all the three are low, all the gene expressions of all the three are low, and the other extreme is all the three are high. And in between, we can have single positives and double positive states. So a combination, so there are 8 possible states here. A combination of these two will give bistability.
But we see that out of these so many possibilities, only 3 are predominant here. Those are arising. And tri-stability, only one combination can be seen, like if you tune in the parameters and all, one of these states are arising, and that is a combination of this ABC, which are the combination of single positives, and one of these. So this is another system where I talked about toggle switch and toggle triad. What we add here is dimerization process. So we have a bath, and in that bath, we now have homodimers, heterodimers, and they're interacting in a toggle switch and toggle triad fashion. So these are snapshots from experiments, and what you see here, this is, if I just reiterate it, so there is A, and they can form homodimers, and that homodimers is autoregulating its way. B is doing the same, and then they're interacting and forming a heterodimer. So in these kind of systems, from even a 2-component system, you get a tri-stability. And this you see, like for 3-component system, you are getting, I guess, from the image that you are getting higher order stabilities. So let's do this mathematically. So dimerization dynamics, we assume that, it occurs, we don't assume that, it occurs on a faster time scale than the protein production and degradation. So we can actually write down these equations, and we write down this formation of homodimers, heterodimers, and just the conservation relations, and we put in, we find those relations, and we put the effective those kind of things here, and find that we can mimic that tri-stability from a 2-component system, both temporally and spatiotemporally. When we add this protein dimerization, when we take into account this protein dimerization in the process. So mathematically speaking, we are including like more nonlinearities and higher order stabilities are emerging. So this is an ongoing work, and from the 3-component system, we can have these kind of even quadra, hexa, and septa stability. So this is a system, another system, like I talked about toggle triad. I'm just doing, like, giving you an overall idea of different kinds of motifs. So finally, maybe we'll do something together and all. So here, what you do, you just have a cycle. So you decrease the strength of one of the links, and you increase the strength in the other way. And what you can generate is a spatiotemporal oscillations in this way. And after, like, you will see that these are not exactly the same. And after 240 time steps, things are exactly same. And these, you can have periodicity in this way. And you can generate biological oscillators. So what we have done, we have created a mathematical framework where we put in these kind of networks and we generate different patterns. So right now, this is a framework and generating different kinds of patterns. And what insights does this give? Like, we'll quantify it, and a lot of things are left. This is an ongoing work, and you can see this is an example of a realistic network for cancer metastasis. Cancer metastasis is basically the process of migration of a small cluster of cells from a primary tumor, breaking apart from the primary tumor, migrating through the blood or the lymph, and going to the secondary tumor, a secondary location for proliferation. So during the migration, or this EMT, this is called epithelial to mesenchymal transition, where epithelial cells transform into mesenchymal. So that means they gain motility. And these kind of things also happen in development and cancer and different kinds of processes. So what kind of patterns this emerge, and what does that mean biologically? And we need to quantify those kind of things, what happens when anisotropy in the diffusion coefficient and all those things. So I'll leave you with this thought, and I would like to acknowledge Mohit, Sumanta, Sayantari, Priya, and a bunch of very brilliant undergrads, Divyo, Chinmay, and Naveen, who were instrumental in doing this work. Thank you. I think I'm very ahead of time. I will be happy to take questions and let's discuss.
Yeah, are there any questions?
Okay, so the So is there a reason why you are putting this toggle switch on a two-dimensional surface instead of putting in three-dimensional and a smaller?
So one thing is that from experiments we get those fluorescent images, right? The one I was showing. So to compare with that and to go like to understand a real validated network, I thought of like, let's start with these motifs.
Just a thing.
Yeah, let's start with the motifs, and then the combination of those motifs gives, like I gave 2-3 examples where you see that these are basically toggle switches. This is a toggle switch, this is a toggle switch. They're coupled in a certain fashion, and they also have auto regulation. So you will see, like I have studied toggle switch separately. I have an auto regulation there. We need to couple different things and see what happens. So yeah.
The other question is, Uri alum, like in the network analysis, it was also known that the feed-forward looks are predominant.
Yes, definitely.
So
I haven't considered feed-forward loop yet. There are that coherent, incoherent feed-forward loop. That is another motif, and that has some biological relevance and functions. But I haven't like today shown that.
Hi. So there's a lot of interest in trying to infer the underlying gene regulatory network if you're given gene expression data, right?
Yes.
So do you know of any situation where if you have this kind of spatial data, gene expression data, are you able to infer what the underlying gene regulatory network is?
That is an unknown thing, because you can generate a pattern from a pure chemical thing, right? Just to chemical species diffusing and you get pattern which might look very similar. You have anisotropies in the magnetic system and you get a similar pattern. So given a pattern, knowing an underlying mechanism is difficult. It's not known yet. So
because I guess where I'm coming at it from is, of course, if you explore a lot of network architectures, you'll get different patterns. That's a given, right?
Yeah.
But then if you have biological data, how do you figure out what is the network driving that pattern?
Right now, that's why we are like exploring the whole, we try to explore it motif-wise and combinations, taking and understanding these kind of things, because this is very new and people haven't done this synthetically also, and even theoretical explorations haven't been done. So given a pattern, what is exactly, so this is like we can match it. Maybe at some point of time, we'll be able to do that one-to-one mapping or something. But that is an overstatement, I guess, right now.
Do you think that it will be possible to map? So you have these different network motifs which you are building up from sort of a bottoms-up approach, and they're generating these patterns.
Yeah, that's the top-down approach is not that easy. Since patterns, you see different kind of systems, and you even in not biology, you get same patterns and all that. So given a pattern, what is the underlying mechanism? That is a question, open question, and no one knows it. So we are just trying to do the other way around, and maybe it's just a guesswork. It will be a guesswork, I think. Because the top-down approach, that is not direct, and we can do our gene mapping if we know. So you were telling we don't know about the biological process and what's going on, right? You just have a snapshot. That's it, right? I think then maybe that will be a data analysis work, right? Right now, the state of the art.
Yes. In your toggle switch, A goes to B or A replaces B. Yes. You also presumably have an interaction between A and A, which would, because it looks like some kind of multi-component phase separation.
I don't have that specific auto regulation here.
How does the pattern arise? Is there a source at that?
So there is no auto regulation in this. I don't consider that is arising because of that repressions and all. So I don't have a specific. You can have self-regulatory loops, sure. And then if you put in full self-regulation, that I have seen that from two-component system also you get price stability.
So, and this is within a cell or is it a tissue?
This is like the network is within a cell. The patterns, what you are seeing is at the tissue level. So you have some intracellular information in context of gene regulatory networks,
but you are looking at tissue level behavior.
Are we considering any intracellular, in this model,
Yes.
you said that in each cell, this kind of gene representation is there. So, are the cells talking to each other?
Yeah, the cells are talking to each other in a diffusive mechanism. The molecules can diffuse across the cells. It can go to the other end of the tissue. But the genetic toggle switch is locally or located within the cell. So what we have is a local reaction and a global diffusion across the tissue. So if you talk about like crosstalks and all that, we don't have like specific sensory molecules binding to the cell or direct endocytosis or those kind of things. But we have a diffusive mechanism which is helping that crosstalk happening and the domains are arising. So you have kind of a long range interactions in that way.
The gene expression in, say for example, gene expression in cell number 5 is affecting the gene expression in cell number, say 25.
Yes, sure.
Is that kind of, possible?
Yes, that's possible. I mean, that's what we are doing. I mean, they are doing that, and we are seeing that the cell is, the membrane is like through the membrane the molecules can diffuse and all that. So cell 5 is definitely talking to cell 25.
So the diffusion coefficient is the key here.
Yes, like how long you want them to talk.
Thank you.
Yeah.
Yes.
So if I remember correctly, that in during instability, the geometry of the matrix, the boundary condition also play a role, so that your tails of a leopard is a different pattern than this thing.
Yes, definitely the boundary conditions and also the diffusion constants. So in Turing patterns, you have to have diffusion diffusion constant of one species should be greater than the other. Right. So diffusivities, and there are like I think five mathematical relations with the reaction terms and diffusivities and all those. And those kind of equations are not satisfied. Still, we are having patterns. That's why, like initial stages, I told like these are multi-stability driven different patterns which are different from Turing patterns. But we need to analyze the instabilities and like one-to-one mapping. So we are getting even like not in the anisotropic case when dA and dB are equal, diffusion constants of both the species, we still get patterns. And also these patterns are transient in nature. In many of the cases, like not if you add protein dimerization, so the time of homogenization that varies from motif to motif. Still, we are in the empirical time scales. We are dealing with motifs and we are having like physics kind of things. We don't have a one-to-one mapping with exact molecules and those kind of things. But in Turing things, that diffusion constant also plays a role. You will not have a pattern when the diffusion constant of the two species are the same. Yeah. We need to understand more about things and do the quantifications.
Are there questions left? If not, then we can thank
you so
our
much.
speaker one more time. And then we move from Pune to Bombay with Ranjit Panditeri. I'm so sorry, I'm not really. Maybe you can pronounce your name one more time yourself. I really apologize for that. It's the last talk of the session and the conference.
Can you hear me? The back? Thank you for the organizers for organizing this and inviting me. This is somewhere in between Mumbai and Pune, with the Western Ghats. And I'm going to talk about predicting chromatin polymer properties from contact probability data. Since there has been probably no chromatin, I will just explain all the terms and what does it mean. So feel free to stop me in between. So as you all know, DNA is the molecule that contains the genetic code. It contains this code ATGC in some fashion, and there is a long code which encodes how to produce material for everything happening in our cell. For example, if we have a wound, how to heal the wound. The material needed to heal the wound is created by reading this code. Or when we eat the food, the code to digest the food, or the material to digest the food, the enzymes needed to digest the food is created by reading this code, right? So the DNA contains the code for almost everything happening in our cell. But if you take two kinds of cell in our body, let us say skin cell or cells in our eye, they are very different. Eye is very different from skin, and they behave very differently. The DNA in both the cells are exactly the same because we started from one single cell, and the DNA is copied during cell division. So all the cells are created from a single cell. The DNA is copied. So the DNA content, the DNA sequence in these two cells are exactly the same, but these cells behave very differently. And it's an interesting question that how do they and why do they behave differently? And the answer to that is related to something called chromatin and how the DNA is folded into chromatin. So the DNA in cells is not bare. The DNA is covered by large number of proteins. So this kind of a DNA polymer is covered by large number of proteins and folded into a structure called chromatin. So chromatin, the word that you will hear, is essentially a structure that's made of DNA, a polymer that is made of DNA and many proteins. This is the kind of more detailed structure of chromatin. It looks something like this, a very long polymer, and the chromatin has multiple layers of information encoded in it. The yellow is the DNA, which has a genetic code on it. And you can see some red dots on the DNA, which is some kind of chemical marks on the DNA called DNA methylation. And that has a particular sequence, a particular pattern, and that encodes some information. And on top of the DNA, there are some proteins, which are the blue colors. They are histone proteins, and this DNA wrapped around this histone proteins are called nucleosomes. So this is some word that I will use often. The nucleosomes are essentially DNA wrapped around some proteins. And these proteins are positioned in a particular fashion. And the way they are positioned encodes some other layer of information. For example, here, they are encoded, positioned differently from here. It's kind of empty here. Here, the blue proteins are positioned differently from here. So the way these blue proteins are organized along this one-dimensional DNA encodes some amount of information. And on top of this blue proteins, there are some flags you can see, the red flags and green flags. These are another set of chemical marks on the histone proteins. They are called histone modifications. Some kind of acetylations, methylations, some chemical marks. And these chemical marks also has a pattern. Some places there will be red, one color kind of marks, and some other places will have other kind of marks. And this marks also encode some information. So this, on top of this genetic code, there are multiple layers of extra information encoded. Almost everything is kind of one-dimensionally encoded information. And this information is called the epigenetic information, and that decides, that differentiates essentially a skin cell from a brain cell or a cells in our eye, right? And this whole thing that is folded in 3D and making all these layers talk to each other. So this is the kind of rough understanding of how chromatin is organized. And this organization is different, slightly different in our skin cell and slightly different in our eye cell. And this difference is what essentially leads to different genes to express, and thereby these cells behaving very differently. Now, if this organization, the three-dimensional organization of this whole polymer is what leads to this different cell types, maintenance of different cell types, it is an interesting question that how is this long polymer is organized in space and time? And this is the question that, a part of the question that we will try to understand. This three-dimensional organization matters because this controls many aspects like gene regulation. There are some processes like recombination, translocation. Even the DNA repair, when we, every day, when we go on sunlight, we get ultraviolet rays, and they kind of break some part of the DNA, and the DNA gets repaired all the time. So the DNA repair, many aspects get influenced by how the chromatin is organized in 3D as a polymer,
And this is the question that we are interested in, how the chromatin is organized in 3D. So as a theorist, the question that we are interested in is, can one accurately predict the three-dimensional organization and the distance between different genes in a chromatin such that we can understand many of these biological processes. So the way, now what does experiment tell us? So the most popular experiments that study the three-dimensional organization of chromatin is called chromatin conformation capture experiments. Those experiments work in the following way. Imagine a polymer in 3D. When two parts of the polymer are in proximity, they can get, the experimentalists can cross-link using some chemicals. So the red dots are some chemicals like formaldehyde. They throw in and cross-link any two parts of the polymer, they are in proximity. Once they cross-link these regions in proximity, you can cut out those, you can cut the DNA randomly at random locations and separate out. Imagine this 4 cuts, then this X part will be separated out. You can separate out these pieces of DNA and then map those to the existing human genome. For example, comparing this sequence with this sequence, you can say that this came from this part of the DNA and this Y came from some other part of the DNA. They can say that, okay, X and Y were in contact. So this is an experimental method which essentially generates a contact matrix. So at the end of a complicated set of experiments, the experimentalists generate something called a contact map, which basically tells you what is the probability that region X of the long polymer was in contact with region Y, which is a very far away segment of the same polymer, right? Or any of the chromosomes. So this is the kind of typical contact matrix that experimentalists get, which has some structure, and it of course a symmetric matrix because contact probability between X and Y is the same as contact probability with Y and X. And this is generated by averaging over many cells. Yeah. Formaldehyde. So yeah, this cross-links the different parts of the. So imagine a polymer. If it comes together somewhere nearby, this is cross-links.
But how does formaldehyde distinguish between the location where it is cross-linked versus where it is not cross-linked?
It doesn't distinguish. It just cross-links wherever two parts are nearby. In 3D, if two parts of the long polymer are nearby, if I have a cable, so they just cross-link. So finally, you will have a cross-linked polymer. And once you have a cross-linked polymer, you cut randomly at random locations. And then you separate out these parts. Then you can purify this and sequence it. And once you sequence, you can map those sequences to a particular part of the genome and generate a matrix. Now, once experimentalists make this kind of a matrix, the question remaining is, how do you go from this kind of a 2D matrix to the 3-dimensional organization of chromatin? How do you generate a 3D polymer configuration from this 2D picture? And this is the question that we were interested in and we have been trying. And one of the important points is that the contact probability is not 1. It is much smaller than 1. It's an order of magnitude smaller than 1. Like 0.1 or smaller than that 0.1 typically, which means that any of these contacts are only happening, if you think of kind of a population picture, these contacts are happening only in 10% of the cells or smaller. So maybe sometimes 1% of the cells. So generating confirmation becomes more complicated because a lot of stochasticity exists in this contact.
Just one question.
Yes.
What is there on the right y-axis?
Oh, this is some, they separated this to a domain A, this domain B, and so on and so forth, which I wouldn't go into the detail, but I can tell you. So this I just took directly this graph from one of the experimental paper where they just separated this to domain A, domain B, domain C, and they gave some name for the domains. This is from one of the papers that I showed earlier called Nora et al. And I can tell you in detail after this talk. Okay, so now if you want to generate this, one has to have a polymer description of chromatin. You all aware of polymer description of DNA. DNA is described reasonably well as a worm-like chain, and we know the persistence length of the DNA. We know the many aspects of DNA as a polymer. The fact that as a worm-like chain model is not extensible and it has no intrinsic curvature. So all of these aspects are kind of well known for DNA, but nothing is known for chromatin. What about chromatin? If you want to study or simulate chromatin, one has to understand some property, some polymer property of chromatin. What we know about chromatin is kind of from biochemistry experiments and some kind of cryo-EM or electron microscopy experiments. So what does electron microscopy and biochemistry experiments tell us? That you have this DNA. DNA is wrapped around these proteins, as I said. So these proteins are called nucleosomes. So the first level of packaging of DNA is wrapping DNA around these proteins, forming a chain of nucleosomes. So these are chain of these nucleosomes, and this unit is called the nucleosome. And then they fold further in 3D with the help of many proteins, making some kind of a complex polymer. So the property of this complex polymer is what we want to understand. And if you take one chromosome, human chromosome 1, for example, there are 1 million nucleosomes. So you cannot even simulate the whole chromatin at the scale of nucleosomes, because then you have to simulate 1 million beads, and which is almost impossible. If you just want to simulate the whole genome, this 23 pair of chromosomes, you'll have about 30 million nucleosomes. And not only that, we neither know the precise interaction between two different nucleosomes. What makes this kind of a structure? What is the internucleosome interaction? We do not know. So we need a kind of a coarse-grained picture, because we cannot simulate nucleosome level. So we have to go from such a picture to a bead spring chain model picture if you want to simulate and study chromatin. So the immediate question that we are interested in is, how do we go from this kind of a picture to this kind of a picture? If you want to go, you have to do some kind of coarse graining. How do we coarse grain this kind of a heterogeneous polymer, and what can we say if we coarse grain? So typical models assume that a few kilobases of chromatin, that is a few nucleosomes. 5 nucleosome is 1 kilobase. So let's say 10 nucleosome is 2 kilobase. A few nucleosomes are considered as a bead and connected by some springs. That's the typical bead spring chain model polymer picture. But we do not know what is the physical dimension of a few nucleosomes. A few nucleosomes can either be very compact, or it can be quite extended. So we do not know what is the physical dimension of a bead in such a picture should be. And we neither know what should be the interaction between the beads, what is the strength of the interaction, how strong this interaction should be. We do not know what is the stiffness of the spring, how stiff the spring should be. We neither know what is the bending stiffness, or what is the bendability of, what is the angle bendability of such polymers. So none of these aspects are not known in this literature, or there is no clear-cut answer to this. What we know very well is something, again, at the structure of a nucleosome, which we know from X-ray crystallography, and we know the dimension of this nucleosome is like 11 nanometers. So it's all the order of tens of nanometers is what these structures are, these beads are. And what we set up to do is to build nucleosome resolution chromatin configurations. And the way we did was, we started with the contact map that I showed. And so recently in 2020, a group in Berkeley published the contact metrics, the contact map, that a similar map that contact metrics that I showed for mouse embryonic cell chromatin at the nucleosome resolution. So basically, they have this kind of a contact map, which any point in this gives you the contact probability between nucleosome I and nucleosome J. So this tells you what is the contact probability between a particular any two nucleosomes. Yeah.
So is this still formal behind, or no? How do they do it?
So just a microfocal nuclease instead of just the cutting enzyme is changed. Instead of a sequence cutter, they would use a microfocal nuclease, can cut everywhere. I'll tell you the details. Yeah. So this contact matrix gives you the contact probability between any two nucleosomes. So now our first aim is to generate a chromatin configuration from this. So we did a simple procedure. We kind of developed a procedure which is essentially, so it has multiple steps, how to go from here to here. Let me simplify for this talk in one step, but I'll be happy to tell you the details after the talk. So the basic idea is that you take any point, let's say the contact probability is around 0.1, we generate an ensemble of configurations. So in that 10% of the case, the contact probability is 0.1. In 10% of the configurations, we put a spring between those two nucleosomes. So go to every point look at the probability, and according to the probability, you put a spring, which would generate these connections based on this contact probability map. But it's not that simple. There are some extra steps which I am not telling you right now. If you just put randomly springs, you will not work. This will not work. And that extra steps, I'll be happy to tell this. And then you equilibrate and you will generate a 3D configuration. So that's the basic idea. Now, once you generate this, of course, you should get back what we put in. So we put in this experimental data, we'll get back similar data. If you have a square here, we'll also have a square here.
The two loops which are far away are connected or not connected?
They are connected, yes.
They can be connected.
They can be connected. So we just put in by hand, right? These are put in by hand. By looking at those experimental contact metrics, we put in by hand. We use some tricks to connect faraway beads, which I am going to tell you later. If they have this faraway interactions, the experimental simulation will also have this faraway interaction. So we essentially get back similar contact metrics as we put in, which is the first check. But then we can check what is the distance between any two beads. If we have an ensemble of configuration, we can look at what is the average 3D distance between any two beads in this. And this average 3D distance between two beads can be computed. So this is the average 3D distance if the two beads are separated by a particular 1D distance. So this is 1D distance, this is 3D distance. And this is done if you look for a specific chromatin. There are some experimental data from some kind of microscopy experiments. So these red dots are microscopy experiments. And this falls on this without an extra fitting parameter because we have only the size of a nucleosome, which is something that we know. So it's not a free parameter. Taken the size of the nucleosome, we can get this falling on the experimental data without any extra parameter. So so we have 3D distance between different genes. So this says, for example, two genes which are 160 kb away are in 3D about 300 nanometers away. This is what this says, right? So we get not only the 3D distance as well as the contact map, which gives us some confidence that we have a ensemble of configurations which matches with whatever experimentally measured so far. So given this large number of configurations that we have, we can systematically coarse grain. So what do we do? So we have a polymer, which one bead is a nucleosome, and we coarse grain this now in the following way. We take a few beads, let's say we take 10 beads. So 10 nucleosomes is 2 kilobases of DNA. We take 10 nucleosomes together and draw a sphere around it. And you ask the question, what is the radius of gyration of that sphere? That will give you the size of 2 kb chromatin. And we can vary this NB. We can take 5 kb, 10 kb and ask what is the size of this many kb of chromatin. Yes.
In the last slide,
yeah,
x-axis and the y-axis.
Yeah.
Like the 3D should be less.
It's different units. It's just a matter of units. Yeah. Yeah. So now we have this configuration, which is the configuration that we obtained, which is from the contact matrix. Then we code grain. So we take a sphere, ask what is the size of the sphere. We can take two neighboring spheres. So now once you coarse grain, you have a new polymer, which is this colored beads here, this big beads. So in this new polymer, we take two neighboring beads and ask what is the distance between them, which is LCG. And since we have large number of configurations, we will have a distribution of LCG. And the width of this distribution essentially gives you the stiffness, the spring constant, or the stiffness, or the flexibility of this polymer. And then we can take 3 beads and look at what is the angle. And if we can compute the distribution of those angles, that will tell us something about the bendability, the bending stiffness of chromatin. So we can compute all statistical properties of chromatin by generating nucleosome level configuration, for which we do not know, we do not need any parameter because we already know nucleosome size, etc., from the crystal structures. And then coarse grain it systematically and ask what would be the properties at much larger scale. So this is the idea that we did. So Sangram did a lot of this work and his colleagues in the lab. And what we get, for example, is the size, the RG, of course, will depend on the genomic location. Some locations are more compact than some other locations. So there is a variability along the genome, but you can find an average of this. So this is what is plotted. The average of this is plotted. The x-axis is the number of nucleosomes that we take, and the y-axis is the average radius of gyration of the sphere. So, of course, if you just take random walk, you will get a scaling 0.6, and we have some controls, which is the random walk, sorry, self-avoiding walk, which is the green, and kind of a highly compact globule, and the chromatin will fall somewhere in between. And we can take different genes. The red color is some set of euchromatic genes, and the bluish color is kind of heterochromatic genes, and one would get different size depending on what is the nature of the local chromatin. So this is, and again, these dots are whatever the experimental data available for this kind of a size. So for about 80 to 300 nucleosomes, there are only few experimental data available. This is from a Chavez 1 group in Harvard. So again, this is microscopy data and no fitting parameter, which kind of falls close to what we obtained. So this again gives us confidence that our answer is indeed sensible. Now we can also look at the LCG, the inter-neighboring distance, which also varies depending on the genomic location. The distribution of this neighboring beats is plotted here, P of LCG, which is not a Gaussian, but nonetheless we take the inverse of this bit and assign it as a spring constant. So from this distribution, one can get a spring constant, which is kBt by the variance. And this is a spring constant for the coarse graining that we do. So if we take 10 kb of chromatin, and the typical spring constant one would get is about 3 or 4 or 5 piconewton per micrometer. Or in a dimensionless unit, it will be about a unit which is shown here, right? So we have now the number which anybody can use in a simulation. If you want to simulate chromatin, and if you want to make coarse grain the chromatin and make beads of 10 kb or 5 kb or 2 kb, what should be the spring constant to use? We have some numbers. What should be the bead size to use? We have some numbers. And the immediate thing that emerges from this is that if you take a 5 kb of chromatin, let us say in red color, and the neighboring 5 kb of chromatin in blue color, typically all the simulations so far would consider these two as two beads interacting with some kind of a Lennard-Jones potential, which means they will never mix. But in reality, you can imagine if you have a long two polymers, they would certainly mix. Entropy would make them mix. Not only here, it's not only entropy, they are interacting. There are intrachromatic interactions like those contact map would show. So they would certainly mix. And we can now, since we have a nucleosome resolution polymer, we can just tell how much they are mixing. And this mixing can be kind of quantified in a few different ways. One way to quantify is to compute something called overlap parameter that we define in a simple way as 2 times the radius of gyration divided by the length, the distance between two neighboring beats. This is one way of defining. And that immediately tells us that there is a lot of mixing and we have some way of quantifying that mixing. There are a few other ways of quantifying by looking at the distance distribution. If the distance distribution is less than 1, that is because they are overlapping. Otherwise, the distance between center of mass distance between them should be 1 or above. So any 2 beats, you can look at the distance distribution, and we can the area under this curve below 1 is a measure of how much they are overlapping, and we can quantify that. And then we can quantify the angle between 3 neighboring coarse-grained beads, and this angle has a distribution. We can also compute the dihedral angles, which is you might have heard of the geometrical angles in proteins, which are basically angles between 2 planes made by 3 vectors. So you have 3 vectors. The first 2 vectors make a plane, and the second and third vector would make another plane. And this angle between this is the dihedral angle. This is what Ramachandran predicted for proteins. So we could measure that for chromatin now. So we could have all this angle distribution. This is an example of an angle distribution for no coarse graining. So this is P of theta, and a different measure is P of theta by sine theta, which is in this measure that a random walk would have a flat curve where all angles are equally probable. So this is the corresponds. So this the gray is a random walk, and the other curves are for different genes, and one would get an angle distribution. This is without coarse graining, and those who are into this, there is a 60-degree angle peak known for nucleosome resolution. So this is something that is known. So with coarse graining, we can get angle distributions. Then the question is, what is interchromatin interaction? And we do kind of an kind of iterative Boltzmann inversion to actually compute the interchromatin interaction. We know some G of R, like distance distributions. We ask the question, what interaction one should put in to get this G of R? And what we get iteratively, we compute this potential, and at the end we would get a potential. It's a soft potential, there is a lot of softness. And using this potential and the spring constant and the all the parameters that we get, if you simulate a coarse grain model, you will get the 3D distance, which is exactly the same or comparable with the fine grain model, which essentially tells you the coarse grain parameters that we got are reasonable. Okay, so this is the coarse graining idea. We have a few other things to predict from contact probability, what is the interaction strength, and so on and so forth, and what is the scaling of the 3D distance with contact probability, etc., etc., which I wouldn't go into the details. So, and just 2 slides just to end that using 3D chromatin polymer nature, we also would, in the lab, we are interested to understand other aspects. You would have seen poster by Vinod, which talks about how the 3D organization would help spreading of certain chemical marks, which this here it could talk to him. And Shruti had another poster which talks about how a protein would do a random walk along this 3D polymer structure, and that would help to find the target. So these are some aspects that we are interested in. So just to summarize, the work that we are interested in is to study to make a quantitative description of chromatin as a polymer, and we computed different properties of chromatin, and we would use then this chromatin polymer picture to study other biological questions. I'll thank all my funding agencies and my collaborators. So this chromatin work is done with Mithun, who is in the department of IIT Bombay, and the Sangram, Kiran, Vinod, and students who are here in this picture, and the other work with my other collaborators. I'll be happy to take questions.
So is your model sufficient to give rise to these A and B compartments, and also the idea that heterochromatin generally tends to be on the periphery, or do you need something extra to get that?
Yeah, to get the periphery part, we need lamin and all that, which we don't have. We have just only gene level description of chromatin.
But even the separation of euchromatin and heterochromatin, would you get it from here?
Which would come because we are putting the contact map by hand. So it is there buried in the contact map. So it will come. So we are not generating that information from any interaction. We are asking a question: if contact map represents the chromatin structure, what are the can we say something about the property of the polymer from that contact map? That's our question that we are interested in. So of course, we start with the contact map, which is experimentally known information. Since that includes A and B compartment, it should emerge.
Have you tried to figure out the Ramachandran plot here explicitly?
Yeah, we have the distributions. Yeah, not 5 sides, but one of the dihedral angle distribution we have.
Yeah, and the ER distributions which you have shown, that looks like those are only gamma functions. Looks like
this one.
Yes.
This could be fitted with the gamma function. We didn't put a lot of effort to fit it, but rather our aim was to just use it for generating the potential. Yeah.
Last question. I will have the last question. So I understand right that these histograms, they appear like this because in the cell the DNA actually changes shape all the time, and then if you look at different cells, you find the DNA in a different structure. That's what it is.
Yes. So the basic idea is that chromatin is different cells are in different structure. So our aim is to understand the property of the polymers and the interaction between them.
And then when you have these regions, they are always very close to the diagonal, and the diagonal is very bright because, well, one part of the DNA is close to itself, of course, but then there are sometimes the squares become rather large around.
Yeah.
So does it also mean, like I'm imagining, you make a loop, and then can it matter which of the loops you close first?
Yeah. So exactly. So this square represents locally the DNA is folded and collapsed into some kind of domain-like structure. And yeah, there are further squares, and it says there are some longer loops and so on and so forth. So this is an average from a population. So there are all kinds of structure averaging give rise to this. So for example, this means there is some long loop between this point and this point. Let's say 31.22 and 31.24.
And then the loops also have to open in a specific order to like unfold.
The order we do not know yet, but what is known is that loops exist. The dynamics nobody has clearly understood. Because most of the experiments can only get the statics because they freeze the cell before doing the experiment.
So then we thank all the speakers of the last session one more time. Let's go for the conference. And then I'll take the chance also to thank the organizers of the conference one more time for this really smooth organization and beautiful conference. And then thank you for
So before we formally end, there are some thanks due. Many people who made this conference possible. So first and foremost, also I speak on behalf of Anudra and myself. So as you all know, the conference is organized by various institutions in Kolkata. So this time it was a team of 8 people from various places. So PK from ISA Kolkata, Rakadi from Calcutta University, Shashi from VCC, and Andesha from RKNU. So on behalf of Ananda and myself, a great thanks to all of them, particularly to Shakuntalati, who handled most of the local business here. It was a huge work for her. And of course, without the money, it would not have been possible. So the funding institutions, SNO Center, ISA Kolkata, IACS, and ACRB. So they helped us very generously, which made this program possible. And then the student volunteers who handled a lot of load. So Indranil, Ritik, Chandradeep, Devraj, and Deposit. I guess most of them are here. And of course, the speakers who accepted our invitations and came here all the way from various places all over the world. And big thanks to them. And the session chairs who handled the day-to-day organization of the meeting. And then there are people who are behind the curtain. So we have Nitaida here, and Shomodeep, Dinesh, and Sanjay, who handle the audiovisual every day. They took turns. And almost all of you sitting here every day from 9 to 6. Then also people from engineering section, particularly Mitali and Lokhi, who handled all the things that have to be done before the conference starts. And the administration, of course, they have helped us a lot in all ways, on different ways possible. The guest house staff, the security staff, and the canteen staff who helped us in running the things smoothly. Gurudas for photography. And finally, of course, the participants, without whom it would not have been possible. So final announcement, we plan to organize the next meeting in 2026, early 2026. So hope to see you all there.
I just wanted to say that the conference is successful. Everybody worked, but particularly the local organizers put a lot of effort. Let's give a big thanks to them.
We discuss here for those people who are leaving tomorrow at guest house. We have at the same place, Bosudhara, where we are having all our meals, breakfast and lunch are organized for you. Because next week, I